A very good morning to one and all. I, Mrs. Usha Jadhav, on behalf of Dr. D.Y. Patil Pratishthan's D.Y. Patil College of Engineering, Akkudi, welcome Mr. Vivek Nivane, a eminent speaker from RMD Sinhagad College of Engineering. Sir is going to conduct a session on microwind with respect to the conduction of various digital circuits like CMOS NAND, CMOS NOR, CMOS inverter, followed by that is MUX using transmission gate and then our 1-bit SRAM cell. Sir is having a very vast experience since from last 12 years in VLSI domain. So on behalf of this Department of ENTC, I welcome you, sir. Also, I welcome all the BE ENTC students from D.Y. Patil College of Engineering, Akkudi. Thank you, audience. Thank you so much. Over to you, Vivek Nivane, sir.
Okay, very good morning, everyone. I can see how many students we do have right now. Okay, it's a good mob over there. 42 candidates, including me and Usha ma'am. Okay, great. For a moment, we will short in a moment. Pardon me. Okay, it's great. So today is Saturday and I am engaging your time in an online session on VLSI. Okay, so I am really sorry about that. Actually, we were planning for the Monday session, but somehow the time was not manageable, and that's why we plan on Saturday morning. So I'm extremely sorry for that. And now I'm going to share my screen. Is my screen visible to everyone?
Yes, sir.
Okay, great. So what we are going to discuss in today's session. We do have group B practicals on Microwind. Microwind is a software which is used for back-end designing. Okay, whenever we say that back-end designing, that necessarily nowadays means we are doing CMOS designing. Yes, indeed. Sometimes we go for custom-made designs where we do have the bipolar transistors as well. Okay, but what I will say in today's microprocessors, 98% of your devices are CMOS devices. Those are your PMOSes and NMOSes. Okay, your MOSFET. And we can say that, okay, so if we do have lots of so many MOS designs in our processors, so when we are learning VLSI, necessarily it becomes our most important task to understand the MOSFET design, how to do it. Okay. So for that purpose, before going to actual discussion, I want to show you two videos. Okay, one video is from the Intel, that is animated video, how they go from the silicon to the final packaging of their processor, and another is what is really inside a processor when we do have a ready-made processor in our hand and we try to zoom into it, how it looks like. Okay, so let us have first video, and let me share my audio as well. Well, let me know whether you are able to listen the audio or not? Is it audible?
Yes, sir. Yes, it's audible.
Okay. So here we do have molten silicon, which is 99.99% pure. And we are now going to make slices out of them. So this one slice is called as a wafer, and we do have lots of chemical processes on that wafer. This is a part of a process which is called as photolithography. Definitely not from our syllabus, but it is very, very important. So now our individual processors are manufactured on the wafer. Let us look how they look like. Looking at the wafer itself, you might have imagined. So if we do have, let us consider in case of i7 processor where we do have 45 billion MOSFETs, and all of the MOSFETs are connected to each other. Okay, all of the MOSFETs are connected to each other. So 45 billion transistors, that means 45 0 0 0 0 0 0 0 0 0 approximately number. Okay, so if we do have so many MOSFETs which needs to be connected together, we will require lots of material. Okay, sometimes gold material, sometimes copper, sometimes aluminum, sometimes composite materials. Okay, alloys. We do have different materials, and if you have observed this frame of video, you do have different layers of the materials and metals, which are nothing but um, just like your tracks on PCB. So over here we do have multiple layers of your tracks. Okay, so in i7 processor we do use 43 different materials, different alloys. Okay, and that is very, very what I will say, that technologically advanced specification to use 43 different materials in a single processor. That is a huge benefit which we are getting out of Intel Foundry. Okay, here there is a new word, foundry. What do you mean by foundry? Okay, foundry is a manufacturing industry, a semiconductor manufacturing industry, and in this world we do have only 5 foundries which can give us the semiconductor devices. Most of them are in Korea. Okay, Korea and Taiwan, and Intel do have their own foundry, but to the surprise, AMD don't have their own foundry. They do not manufacture. They design their processors, okay, but they do not manufacture their own processors. They need to outsource them. Okay, so it is a costly affair to have a foundry. Okay, so let us go through the video. So this is an view for, okay, we have cut down the individual processors. At actual, the hexagon never runs on the wafer. Okay, it is shown for the representation purpose only. The wafers are cut down, the processors are cut down from the wafers by using laser cutting. Now a robotic arm is picking up the individual die of the processor, and here comes the packaging, and it goes to the market. Okay, this was a kind of introduction video कि भाई कैसे होता है. एंड इफ वी से दैट ओके यार, सिलिकॉन तो फ्री ऑफ कॉस्ट है, अपने पास तो राजस्थान में बहुत सारा सिलिका पड़ा हुआ है. सो मेक 99.99% प्योर सिलिकॉन from out processors, तो ऐसे नहीं होता. It never goes that way. Okay, you do have lots of things associated with the processor manufacturing. Okay, starting from the design, and for your curriculum you are at the core logic of design. If you are thinking like, oh yes, I am going to for MS, okay, over there VLSI comes under the electrical engineering, and you can do the VLSI design, backend design course over there. One of our students went for VLSI, and he was an average student. I am not saying that he usually got the first class or he usually got the pass class. No, he was an average student, near to 60, and in between the 59 to 62. He always had the marks over there. Okay, and he did his MS, I guess in Paris, I guess. Okay, and he did his MS in VLSI, and that too in backend design. And after 2 years, he got an package of somewhat, I guess, 45 or 45 lakh per annum. Okay, and that is a okay package for an VLSI designer when you go for abroad. Okay, in India, if you try to get a VLSI job, definitely we do have AMD, we do have Intel, we do have Xilinx, Altera, and then Freescale, lots of companies in India, but all the companies are Bangalore based or Hyderabad based. Okay, you need to relocate, and to get employable in those companies, once again you have to go for MS or MTech programs, and another option is you can go for some 6 monthly full-time course, which will teach you VLSI design in a very depth. Okay, 12 hours a day or 14 hours a day curriculum. Okay, so you can make your job over there. So this is how your VLSI industry goes, and money runs your VLSI industry. You do require lots of money, and that's why there are less development projects in India. But yes, we do have very nice support system for the VLSI. Okay, now let us move to the next video, and we will see how our processor looks from inside. Okay, the title says zoom into a microchip processor. Okay, let us say this is a very old processor, but it gives very good insight. Okay, very good insight. Let us see. So this is a usual black color packaging you look
Sorry
for
to
your
interrupt
ICs.
you.
Yes,
So video
sorry.
is not audible. So
It
video
do,
is not visible.
uh, is video visible?
Yes, sir. It's clearly visible.
Okay, the
Yeah.
video don't have any music, nothing. It is a just plain video. Okay, so you won't be able to hear anything. So this chip is being scanned by electron microscope. Okay, so we are going to go into the chip and let us see how it looks like. Can you see some wires running over here? These are the golden wires. Okay, many times the manufacturers use the gold material to have these wires, okay, these boundings for the internal core. This is the internal core, and to be connected to the external pins of the packaging. Okay, that's why person comes to you and say that, okay, we are very environment friendly people and we are going to collect the electronic waste from you, which is very harmful to the environment. No, they are bluffing. They are going to collect. Okay, I will pause the video. They are going to collect the e-waste from you under the name of environment, and there is whole billion-dollar industry running at the back end, which extract lots of material from your e-waste. They extract plastic, they extract rubber, they extract copper, they extract aluminum, they extract gold, everything. Lots of materials are there. Okay, so whenever a person stands in front of you and says, hey, I am environment person and I am going to collect e-waste for the sake of saving the environment, he is bluffing. He is just making money out of your e-waste. Okay. Now let us zoom into our microchip, and you can see the slanting line over here is actually having physical dimension of 1 millimeter. So you can see that, okay, in 1 millimeter by 1 millimeter area, we do have lots of things running over here. And let us zoom in more into our microchip. We are scanning the chip by using electron scope. So after more resolution, when you go into the more resolution, you will see everything black and white. Okay. So can you see lots of lines running here and there, running here and there, crossing each other? And can you visualize those are actually not connecting each other, but those are running over each other. Okay. एक दूसरे के ऊपर run कर रहे हैं वो tracks or wires. Okay. And let us zoom into more. Okay. Now, can you see some dot over here? Some circular region over here? Oh, slightly circular. Okay. Some circular region over here. Can you see my mouse pointer? Can you see my mouse pointer?
Yes, sir.
Yes, sir.
Okay. Okay, great. So here we do have some circular region. We do have a little circular region. We do have some dots. Okay. So actually these circular regions over here, you will find lots of circular region like this. These are connecting the different planes of your tracks. Okay. Connecting wires, connecting materials. I will discuss this one once again. I will show you a diagram. I have pasted it into the PPT. And whenever we want to connect one plane to the another plane or one track to the another track, point number one, we are going to use different materials. Point number two, whenever we want to connect different materials, we have to use the contact. Okay. And point number three, this contact is called as via, VIA, via. Okay. We will discuss that one in the diagram. So right now we are in the range of micrometer, and the white scale over here has a physical dimension of 6 micrometer, 6 into 10 raised to minus 6 meter. Okay. Now we are in the range of 1 micrometer, and you can see that, okay, one track width, okay, one track width is of 1 micrometer, that is 1000 nanometer. Okay, 1 nanometer is equal to 1 into 10 raised to minus 9. Okay, the diameter of atom goes as 1 into 10 raised to minus 10, or I will say that angstrom. Okay, so we are so much near. So I can say that, okay, in this width, we do have nearly 1000, I will say that nearly 1000 atoms. Okay, nearly 1000 atoms in the width of a track. So you are doing so minute level design. Okay, so that becomes very interesting. Okay. And okay, let me go, let me see whether I do have some interesting over there. Okay, no, fine. So when we talk about the backend, this is what we are actually designing. Okay, this is what we are actually intended for. Definitely when we go for a design of 45 billion transistors or MOSFETs, it is not a full custom design. Okay, we do have a different types of design. One is full customs, another is semi custom. Okay, so full custom मतलब एक एक MOSFET लेके मैं खुद डिजाइन करूंगा. And another type semi custom, okay यार ये एक एक MOSFET लेने से अच्छा तो मैं क्या करता हूँ, readymade library लेता हूँ, and we will use that library. I will write down some piece of program just like VHDL program, and I will convert that into the MOSFET level design. using some sort of EDA tool. तो आपके पास वो EDA tools होते हैं. तो EDA tools कितने महंगे होते हैं? For academic purpose we use those kind of backend EDA tool with an क्या कहते हैं उसको, discount of near about 97 to 98%. ओके, कितना डिस्काउंट है? 97 to 98% डिस्काउंट है. मतलब 100 रुपए की चीज आपको 2 या 3 रुपए में मिलने वाली है, बीइंग एकेडमिक इंस्टीट्यूट. और उसका ईयरली लाइसेंस, ओके, ईयरली लाइसेंस होता है लगभग 23 to 24 लाख रुपीस. ओके, सो दिस इज द कॉस्ट ऑफ टूल विच इंडस्ट्री यूजेस. तो भाई अगर 2 या 3 रुपए की चीज मतलब 23 या 24 लाख रुपए देने पड़ रहे होंगे, तो सोचो कि इंडस्ट्री को लाइसेंस कितने में होता होगा, मतलब द कॉस्टिंग दे आर इन्वेस्टिंग. ओके, सो आफ्टर लुकिंग एट दीज टू वीडियोस, लेट अस गो टू आवर पॉइंट वेयर वी वेर डिस्कसिंग अबाउट द वाया. ओके, तो फुल शो करता हूं. सो नाउ यू कैन सी we do have lots of layers. Okay, and now you can see this vertical cylinder, this vertical cylinder, this vertical cylinder, or this vertical cylinder. Okay, you do have lots of vertical cylinders. Those are actually connecting one plane of the track. Okay, you can see this is the vertical cylinder, this is another vertical cylinder. Okay, all these are connecting one metal to another metal. Okay, and these are called as via. This is a three-dimensional view for your IC. ये जो blue region है, it is called as wafer. Okay, ये जो है, now you know that polysilicon भी material होता है. Okay, then you do have some sort of metal 1, then we do have metal 2, then we do have metal 3, and so on. And the in between we do have the via or contact. Okay, to have the connection in between the two different metal layers. Do remember that metal layers.
Vivek
Yes,
sir,
ma'am.
sorry to
Yes.
disturb. Those who have joined through mobile phone, I think they are not able to see the video. Is it so, students? Let me know.
Yes, ma'am.
Okay,
Yeah.
can you see? Okay, can you see my PPT right now? I am scratching on the PPT, something like that.
No, those who have joined through mobile phone,
Okay.
because I tried through mobile phone just now, but they
Okay.
are not able to see the video.
Okay, let me, I will stop sharing and I will once again share
Can
my
you turn
screen.
on the camera, sir, so that
Okay,
with
I don't have the webcam with me. I
okay,
am
okay,
doing on the desktop.
okay, no problem.
Let me share my screen once again. Now, can you see the PPT? The students with the mobile.
Yes, ma'am. Now we can see.
Okay, okay. So I was scratching on the PPT. So for just एक बार फिर से बता देता हूँ. You can see a vertical cylinder over here, vertical cylinders over here. These are called as via. Okay, VIA. Those are used to connect the different layers of the material. Okay, or tracks. You can see you do have different layers. Therefore, we do require the via. So we do have one via over here, another via over here, third, and so on, so on, so on. So we do have metal 1, metal 2, metal 3. We do have different metal layers. And whenever we want to connect different metal, we will require contact or via. Okay, तो इतना याद रखिएगा. Then the blue one is called as wafer, that you have seen in the video. Then according to the construction of MOSFET, we know that we do have a polysilicon material as a gate material for our device. So what we will do, we will first talk about the MOSFET. Okay, can someone tell me the full form for the MOSFET? MOSFET stands for?
Metal oxide semiconductor field effect transistor.
Yes, perfect. Metal oxide semiconductor field effect transistor. ओके, तो इसको थोड़ा सा ब्रेक डाउन करते हैं. मेटल भी है, ऑक्साइड भी है और सेमीकंडक्टर भी है. ओके, वी विल रिक्वायर metals to have the connection. We will have the oxide material as a gate material. Okay, semiconductor, our N and P regions will have the semiconductor properties. And the next word is field effect transistor. इसके मायने क्या हुए? If you look into the cross section view of a MOSFET, आपने ये बहुत बार देखा होगा, फर्स्ट ईयर में भी देखा होगा, फिर सेकंड ईयर में भी देखा होगा. Okay. So until and unless I write down over here something, I cannot describe which type of MOSFET this is. Okay. If I write down, okay, here we do have N plus diffusion, we have N plus diffusion, and this is a lightly doped P material, which is called as P substrate. Okay, then now I can say that this is going to be N MOSFET. Okay, because our current is going to flow through this region. Okay, लेकिन ये current flow कब होगा? We know that this terminal is a body terminal or a substrate terminal, or it is also called as bulk terminal. This is definitely a gate terminal. Okay, this can be source or drain, and this can be source or drain. Okay, after we apply the voltages, then and then only we can specify, okay, this terminal is drain and this terminal source, or vice versa. Okay, but till the moment we are not applying any voltage, we really cannot say which terminal is source and which terminal is drain because of the perfect symmetry of your MOSFET design. Okay, MOSFET device. तो समझ लीजिए कि भाई चलो अभी इसको थोड़ा सा मैं मॉडिफाई कर लेता हूँ, थोड़ा सा इरेज करता हूँ. तो इसको बनाते हैं सोर्स एंड इसको बनाते हैं ड्रेन. Okay, means this region, the source region, is going to source the electrons. Okay, and those electrons are going to drain into the another region. लेकिन ये चीज होगी कब? Do remember that whenever आपको ये पता होगा कि भाई जब तक ये 0.7 वोल्ट गेट वोल्टेज नहीं लगाते तब तक आपका मॉसफेट ऑन नहीं होता. 0.7 ही क्यों? वो आदत पड़ गई है कि भाई 0.7 कहने की. भाई अगर एन टाइप मटेरियल है तो 0.7 इज द योर थ्रेशोल्ड वोल्टेज. हमेशा ट्रू होगा ऐसी कोई बात नहीं है. डिपेंड्स ऑन योर डिवाइस कि 0.7 है, 0.68 है, 0.6 है, 0.4 है. डिपेंड्स, टोटली डिपेंड्स ऑन योर design. So for an example, we say that, okay, when gate voltage is greater than or equal to 0.7 volt, then your device gets turn on. तो आपका device on होता है. Exactly क्या हो रहा है? Whenever we are going to apply the gate voltage, we will have some polarity on one side of the polysilicon material. ये क्या है? ये है आपका पॉलीसिलिकॉन मटेरियल है. दैट इज अ SiO2 मटेरियल, ऑक्साइड मटेरियल. तो वोल्टेज लगाने के बाद यहाँ पे पॉजिटिव चार्ज होगा, यहाँ पे निगेटिव चार्ज डेवलप होगा. ओके, ये निगेटिव चार्ज क्यों डेवलप होगा? वन, इट इज काइंड ऑफ कैपेसिटर एनालॉजी. ओके, कैपेसिटर एनालॉजी. आपको पता है कि भाई एक प्लेट पे अगर पॉजिटिव चार्ज लगाते हो तो दूसरे पे ऑटोमेटिकली नेगेटिव चार्ज डेवलप हो जाता है. इलेक्ट्रोमैग्नेटिक्स में भी पढ़ा था गॉस लॉ करके. ओके, सेकंड, यहाँ पे फील्ड इन्वर्जन होता है. मतलब क्या होता है एग्जैक्टली? ये जो पॉजिटिव लगाया ना, ये जो पी सबस्ट्रेट था इसमें क्या थे? निगेटिव भी थे, लेकिन ये माइनॉरिटी कैरियर्स है. Am I right? These minority carriers are gets attracted towards your gate terminal due to the applied positive voltage. और वो सारे negative charges यहाँ पे accumulate हो जाते हैं. Okay. Previously this material was P substrate, that is P type of ions are more. Okay, but negative charges are also less. Minority carriers. All those minority carriers get collected near the surface of your material, or I will say the boundary between the P substrate and the SiO2 material. Okay, यहाँ पे आके इस बाउंड्री पे आके ना वो सारे कलेक्ट हो गए. तो यहाँ पे बहुत सारे इलेक्ट्रॉन जमा हो गए, तो इसको कहते हैं फील्ड इन्वर्जन और चैनल इन्वर्जन. ओके, चैनल इन्वर्जन भी कहते हैं. तो एक बार अगर मैं कहूँ कि भाई यहां से लेके यहां तक ये पूरे इलेक्ट्रॉन्स जमा हो गए, so can I say that effectively this n plus region and this n plus region get connected together, get shorted together? So due to under the influence of applied field, first is gate voltage and second is drain voltage. Under the influence of these two voltages, our electrons will start moving from this source region and will go to the drain region. Okay, so ye then what we will say that we have the channel creation, and after channel is created, then our device gets turned on. Okay, तो ये है आपका MOSFET, and you know that how we represent the NMOS and PMOS. Okay, उनका symbol कैसे होता है? So we do have NMOS and we do have PMOS. Okay, so to represent PMOS, we do put a bubble over here. This is a PMOS, this is a NMOS. These are symbols. Now I do have a problem with this design. Let me show you that problem. So we have, right. We have our wafer, a big wafer. Okay, and let us assume that this wafer is of P type. So we call it as P substrate. Okay, तो उसका body terminal, bulk terminal या substrate terminal तो ये बन गया. Now here we want to fabricate, we want to manufacture the N MOSFET. तो यहाँ पे N diffusion, N plus diffusion डाल दिए, यहाँ पे polysilicon डाल दिया. We get the 3 contacts. Okay, तो ये तो बन गया आपका N MOSFET. अगर मुझे P MOSFET बनाना है तो बाय डिफॉल्ट क्या आएगा कि भाई एक P plus diffusion pour करेंगे, बनाएंगे, एक another P plus diffusion बनाएंगे. We will put our gate terminal and all the required contacts. तो ये बन गया PMOS. Okay, ऐसे दिमाग में होता है कि N plus diffusion बनाते हैं तो NMOS, P plus diffusion बनाते हैं तो PMOS. लेकिन अगर यहाँ पे देखोगे आप तो यहाँ पे प्रॉब्लम है PMOS के लिए. What happened? Okay, तो ये है P plus, ये है P plus और ये भी क्या है? P type है. Am I right? Lightly doped है लेकिन P type है. So ये भी कनेक्ट हो गया, ये भी कनेक्ट हो गया. So everything is actually shorted. तो यहाँ पे कोई MOSFET तो बनेगा ही नहीं क्योंकि ours is P substrate and then we have P plus region. Everything is same material, P type material, so everything get short. So क्या करें? अभी ऐसे तो नहीं कर सकते पर सबस्ट्रेट में कि भाई कहीं पे P सबस्ट्रेट बनाया, कहीं पे N सबस्ट्रेट बनाया, ऐसे नहीं होता. पूरा का पूरा जो वेफर है वो एक ही होता है आपका. ओके, एक ही टाइप का, आइदर N टाइप का बना लो या फिर P टाइप का बना लो. Okay, you have to have only one type of material in the substrate. तो क्या करें? So for this we do have one solution. क्या है solution कि भाई अगर आपको अभी बनाना ही है P type MOSFET और P MOSFET तो क्या करेंगे? यहाँ पे पहले ना एक एनवेल क्रिएट कर लेंगे. मतलब P टाइप सबस्ट्रेट में क्रिएट किया एनवेल और इस एनवेल के अंदर P plus डिफ्यूजन क्रिएट किए. सो नाउ वी डू हैव डिफरेंट मटेरियल्स. तो N मटेरियल है, बाद में P मटेरियल है, P मटेरियल है. सो वी कैन हैव द P MOSFET एंड फॉर दिस P MOSFET this is going to be its body terminal. For N MOSFET this is going to be its body terminal. Okay, और अगर अब ये आपने जो देखा वो है आपका क्रॉस सेक्शन व्यू. ओके, तो क्रॉस सेक्शन व्यू को अगर मैं कहूँ कि अभी मुझे टॉप टॉप व्यू निकालना है. ओके, सो फॉर गोइंग फॉर टॉप व्यू लेट अस से फर्स्ट ऑफ ऑल वी विल ट्राई टू ड्रॉ द 3D व्यू कि भाई 3D व्यू कैसे दिखता है. सो वी डू हैव सम रेक्टेंगल व्हिच इज पार्ट ऑफ योर वेफर. ओके, and we will have some material running over here and there. Okay, so please be with me for my 3-dimensional diagram. I am really not good at the 3-dimensional diagrams, but let me try it. Okay, great. Let me erase one line. Okay, So I am trying to draw a three-dimensional view of a MOSFET. Okay, so this is a p-type, this is n plus, this is n plus, and this is throughout your material. Okay, this rod, this is your polysilicon rod. Okay, here you have n diffusion, here you have n diffusion, and you have the wafer. So if I try to draw the top view for this n MOSFET, okay, n MOSFET के लिए अगर मैं टॉप व्यू निकालने की कोशिश करूं तो I do have this polysilicon material, okay, and I do have one n plus diffusion on this side and another n plus diffusion on this side. Okay, and whenever I want to have the contact in between the diffusion and the material or metals, we will put some contacts. The rectangle with a cross indicates it is a contact. Okay, this is n MOSFET. Okay, now if we go to back, we do have extra n well over here. I will try to draw the top view of your P MOSFET here itself. Okay, how it will look like. So first we will draw our polysilicon material. Okay, on the both sides of the polysilicon material, we do have P plus diffusions. Okay, P plus and P plus diffusions. Okay, this is P plus, this is P plus, this is polysilicon. And if you want to have the contacts, okay, we have to place contacts in between the diffusion and the metal. And the P plus diffusions are surrounded by your N well. So we will have complete PMOS design inside a N well. ओके, तो ये बन गया इसका टॉप व्यू. इन दोनों चीजों को आपको ध्यान में रखना है कि PMOS का टॉप व्यू ऐसे दिखता है और NMOS का टॉप व्यू ऐसे दिखता है. ओके, नाउ लेट अस टॉक अबाउट द डायमेंशंस. कि भाई MOSFET की डायमेंशंस कौन सी होते हैं. आई विल हेल्प यू विथ वन डायमेंशन. दिस इज width of the MOSFET. Now I will give you two options for the question. Question is, what is the length of MOSFET? Whether this is the length, option number 1, or you do have some different kind of length dimension. Can anyone suggest? कि भाई ये जो मैंने क्वेश्चन मार्क निकाला है ये लेंथ हुई या फिर कुछ अलग हुआ, कुछ अलग लेंथ होगा. I want to ask you what is or where is the length of the MOSFET. जैसे मैंने width indicate की वैसे length indicate करनी है. ओके, तो कौन सी होगी जो मैंने ऑप्शन दिया है, ऑप्शन नंबर 1. इज इट करेक्ट, यस और नो? देखो एक ध्यान में रखिए, मैं आपको नहीं देख पा रहा, आप भी मुझे देख नहीं पा रहे हो. एम आई राइट? आई कैन हियर द वॉइस ओनली. और किसको पता चलना है कि किसने आंसर दिया. तो डेफिनेटली यू कैन आंसर द क्वेश्चन इवन इफ द यू आर नॉट कंफर्म अबाउट द आंसर कि यार सही है कि गलत है. सो ओनली इट इज द गेसेस. इज ऑप्शन 1 करेक्ट और नॉट, yes or no? Okay, I will go through the answer now. The option 1 is definitely wrong. It's not the correct length of the MOSFET, but this is the length of the MOSFET. Okay, do remember that here in this region everything happens. You apply the gate voltage, your channel inversion occurs, आपके सारे electrons वहाँ पे accumulate होते हैं, then your MOSFET turns on. This is your channel length. Okay, this is the length of your channel and therefore it is called as the length of the device. कि उसी region में जो होता है वो सब कुछ होता है. So in the top view of your N MOSFET, the width of the polysilicon is length of the MOSFET and the height of your diffusions, N diffusion or P diffusion is the width of the MOSFET. तो ये ध्यान में रखना बहुत जरूरी है. So we have a new word over here, channel length. So I can say that the region in between the two diffusions is called as channel length. नाउ अभी आपको पता होगा कि ये जो सारे माइक्रो प्रोसेसर्स आते हैं इंटेल के, एएमडी के, ये हमेशा न बहुत बढ़ा चढ़ा के बात करते हैं। यस, वी डू हैव 32 नैनोमीटर डिजाइन टेक्नोलॉजी। ओके, design technology. We have fabricated, we have manufactured our processor using 32 nanometer. तो यार ये एक्चुअली ये क्या कहना चाहते हैं 32 नैनोमीटर? राइट नाउ दे आर इन द रिसर्च एरिया ऑफ 7 नैनोमीटर। 7 नैनोमीटर के प्रोसेसर्स तो आउट नहीं है, लेकिन इंडिविजुअल आईसीज जो है उनके डिजाइन वो आउट है। आउट है मतलब मार्केट में अवेलेबल है। 7 नैनोमीटर मतलब कितना हुआ? 7 इंटू 10⁻⁹। ओके, इतना है। So I can say that 70 into 10⁻⁻10, or I can say that 70 atoms occupy in a channel. Very interesting stuff is going on over here. All students pay attention. Now our channel length has only 70 atoms. Isn't it fantastic? And isn't it very dangerous? Why dangerous? I will tell you. But can you think that you can manipulate the field? Okay, the field generated by the gate voltage. The field generated by the gate voltage, you are going to manipulate it on the 70 atoms only. How fantastic it is, and why it is dangerous? Because whenever we are going to have small and small and small and very small designs, those becomes very much susceptible to your shocks. कौन से shocks? Voltage shocks, spikes, okay, even your solar radiations, okay, those are more susceptible to heat as well. Okay, you do have lots of things, and if we send these kind of designs into the spacecraft or satellites, there वहां पे तो बहुत सारी solar radiation है। okay, तो उसको कहते हैं सिंगल इवेंट्स। ओके, कि एक सोलर रेडिएशन का हिट हुआ और आपका डिवाइस डैमेज, खलास, बर्न्ड, डाई, ब्लैक हो गया वो पूरा। ओके, and this is one of the reason when you were doing the practicals of digital electronics. ओके, आपके जो फैकल्टी है, आपके जो लैब असिस्टेंट है, उन्होंने बताया होगा आपको कि भाई आप उस पैकेज को पकड़िए, ना कि उन पिन्स को, पिन को टच मत कीजिए, उन्होंने बताया होगा। तो तब मतलब उसका मायने नहीं पता थे यार ऐसे क्यों बोल रहे हैं। आप जस्ट कैसे करते थे कि भाई 2-4 आईसीज उठाए, उनको हथेली में रखे और वैसे ही लेके आप चले गए आपके किट के ऊपर, एंड यू मीन्स unintentionally touch the pins of your IC packaging. क्या हो रहा है? आप पिंस को टच कर रहे हो, यू आर टचिंग द पिंस ऑफ द IC. डू रिमेंबर दैट IC के अंदर क्या है? आपका मॉसफेट है। ओके, एवरीवन डू हैव द बॉडी वोल्टेज, बॉडी वोल्टेज है सबका। लेट अस से फॉर एन एग्जांपल, एक बंदे का 1 वोल्ट है बॉडी वोल्टेज। ओके, एंड आई डू हैव MOSFET inside that IC, a tiny small MOSFET which has a channel length of 1 micrometer. Okay, अभी ये तो पता है कि भाई जो पिन है those are going to be gate terminal of that MOSFET. Okay, तो गेट पे कितना लगा रहे हो आप वोल्टेज? 1 वोल्ट लगा रहे हो. So that 1 volt voltage is effectively is applied to the channel length, and its length is 1 micrometer. So now pay attention towards the wordings. You are applying 1 volt to the channel length, and the channel length is of 1 micrometer. So I can say that 1 volt per 1 micrometer, or I will say that I will write it down numerically. This is something like that. Volt per meter. This is nothing but 1 into 10⁶ volt per meter, or I can say that 1 megavolt per meter. So बताओ अभी वो IC में MOSFET हो है, वो जिंदा रहेगा या कि मर जाएगा? Definitely, if you are applying so much megavolt to a tiny small MOSFET, तो वो तो डेफिनेटली मर ही जाएगा। एंड दैट इज व्हाई द रीजन जब फाइनल एग्जाम्स आते हैं आपके फैकल्टी नए आईसीज मंगवाते हैं कि भाई वहां पे आपके कोई खराब आईसी ना रहे। ओके, एंड डेफिनेटली पहली बैच का प्रैक्टिकल का आउटपुट आ जाता है और दूसरी बैच से प्रैक्टिकल का आउटपुट नहीं आता, क्योंकि पहली बैच के स्टूडेंट्स के हाथ लगे हैं उनकी पिंस को और सम ऑफ द मॉसफेट माइट हैव गॉट डैमेज। और क्या कहते हैं अपन एज अ स्टूडेंट, क्या यार खराब माल लेके आए, एक भी प्रैक्टिकल का आउटपुट नहीं होता। नो बड़ा, द रीजन इज this handling of the ISIS. Okay, so after discussing, let me write down what we have discussed till date. Okay, we have seen a video on the manufacturing and we have also seen how our processor looks from the inside. Then second, we have seen how NMOS and PMOS are fabricated on a wafer, जो diagrams we have seen. Okay, थर्ड यहाँ पे क्या देखा था सेकंड पॉइंट में, व्हाई वी डू रिक्वायर एनवेल। ओके, देन फोर्थ वी हैव सीन द 3D व्यू of NMOS as well as we have seen the top view of both NMOS and PMOS. Okay, इतना देखा है। Then 6 we have seen what do you mean by channel length. Okay, and also we have seen the dimensions of our MOSFET. ये सारी चीजें डिस्कस करना जरूरी था, क्योंकि यहाँ पे चैनल लेंथ में मैं टेक्नोलॉजी भी लिख देता हूँ वर्ड, क्योंकि we will require the understanding of all these 7 things while doing the practical. 8th है, now I want to go for CMOS design. Okay, CMOS design में क्या है? What is the full form for CMOS? It says that complementary metal oxide semiconductor. मतलब क्या? Necessarily number of जितने PMOS है is equal to number of NMOSes. मतलब अगर आपके डिजाइन में 5 PMOS है और अगर 5 NMOS है तो ही आप उसको कहेंगे CMOS टेक्नोलॉजी। अगर आपके डिजाइन में 4 PMOS है और 7 NMOS है तो उसको CMOS नहीं कहेंगे। Always necessary condition is number of PMOS and NMOSes must be same for applying or implementing your logic. Okay, जो logic है आपका उसके अंदर number of PMOS and NMOS must be same. Next, CMOS always provides complemented output. मतलब क्या? हमेशा inverted output रहेगा उसका. Okay, so whenever we are going to implement our design, first design is inverter. Okay, it says that y is equal to a bar. Next design is NAND. Its output equation is AB bar. Next design is NOR. Its output equation is A plus B bar. Okay. One moment, please.
Yes, students, have you understood up till now?
Yes, sir.
Okay, I am back. I had a phone call from the college. Okay, so every time you see, you do have the complemented outputs. Okay, so whenever I want to implement for an example, okay, for an example, I give an expression y is equal to, let us say, AB plus BC plus ABC kind of stuff. This is not the complemented output. So you need to do De Morgan's theorem. Do you remember from the digital circuits, digital electronics? तो भाई आपको ऐसे कॉम्प्लीमेंट कर इसको सॉल्व करना पड़ेगा. क्या होता है फिर अभी? कॉम्प्लीमेंट ऑफ द सम इज मल्टीप्लीकेशन ऑफ द कॉम्प्लीमेंट्स. मतलब ए बी बार डॉट बी सी बार डॉट ए बी सी बार एंड होल कॉम्प्लीमेंट. ओके, तो यहाँ पे फिर आपको थोड़ा सा सॉल्व करके, ये तो y ही रहा, डबल कॉम्प्लीमेंट है, तो हमेशा आपको इस फॉर्म में, इन्वर्टेड फॉर्म में आपको आपका इक्वेशन, जो भी बुलियन इक्वेशन है, आपको वो लाना है. ओके, so as long as our practicals are concerned, okay, there is very simple procedure. First, circuit. Let us not go circuit. First, write down the Boolean equation. ऐसे करते हैं. Okay. तो प्रोसीजर क्या है? First is write down your Boolean equation. Second, उसके लिए schematic बनाओ. स्कीमेटिक कैसे बनाते हैं वो भी आसान है, अभी पता चल जाएगा आपको तुरंत. आधे घंटे में तो आप एक्सपर्ट हो जाओगे, कोई दिक्कत नहीं आएगी. ओके, स्कीमेटिक के बाद एक यूलर्स पाथ होता है. ये क्या होता है? ये थोड़ा सा सॉल्व करते करते आपको समझ में आ जाएगा. ओके, यूलर्स पाथ होता है. इस यूलर्स पाथ में कॉमन पाथ आइडेंटिफाई करना होता है. देन ड्रॉ स्टिक डायग्राम. ओके, ये स्टिक डायग्राम भी क्या है वो भी पता चल जाएगा. और बाद में यू विल स्टार्ट योर माइक्रोविंड डिजाइन, माइक्रोविंड सॉफ्टवेयर, एंड यू विल ड्रॉ द लेआउट. ओके, तो ये पॉइंट नंबर 3 एंड पॉइंट नंबर 4 आर रिक्वायर्ड टू ड्रॉ द स्टिक डायग्राम, एंड स्टिक डायग्राम इज रिक्वायर्ड टू ड्रॉ लेआउट. स्टिक डायग्राम ड्रॉ किए बिना आप लेआउट ड्रॉ नहीं करोगे. ओके, वेरी इंपॉर्टेंट. व्हाई? दिस इज अ सेंटेंस ऑफ एक्सपीरियंस कि भाई स्टिक डायग्राम ड्रॉ किए बिना अगर मैं लेआउट ड्रॉ करने के लिए जाऊं तो आई विल गेट स्टक समवेयर. ओके, you can definitely have an experience at your end when you are going to have the practice, but this is the procedure. Okay, simple straightforward procedure. और जैसे मैंने कहा कि भाई आप आधे घंटे में मास्टर हो जाओगे. कैसे? लेट मी शो यू. तो पहला इंप्लीमेंट करते, लेट मी ऐड वन मोर स्लाइड. I ran out of the blank slides. Okay. So now we are starting with the first design of Group B practicals, Backend practicals, inverter. Okay. Inverter मतलब आपका NOT gate. Okay. NOT gate है. तो क्या चीज होती है आपकी NOT gate में? It has first step. It has Boolean equation of y is equal to a bar, where y is output and a is input. Okay. Second, इसका schematic draw करना है. Since we are doing for the first time, we will analyze the schematic. Okay. तो schematic में draw करता हो. Please observe. So we do have two MOSFETs, P as well as N, and we do have input A and output Y. We do have the drain voltage and we do have the source ground. Okay. So देखते हैं. Now, before analyzing the schematic, let us draw one table. Gate terminal and the status of PMOS and NMOS. Okay. तो status क्या है और gate terminal, इनका relation मैं लिखना चाहता हूँ. If gate is at logic 0, okay, logic 0 है तो PMOS होगा on, NMOS रहेगा off. और गेट पे अगर लॉजिक 1 है तो PMOS होगा आपका ऑफ और NMOS होगा आपका ऑन. लॉजिक लेवल यूजुअली रेफर्स टू द 5 वोल्ट. ओके, 5 वोल्ट लेवल. तो ये टेबल इंपॉर्टेंट है. ओके, सो देखते हैं. वी विल एनालाइज नाउ. लेट मी हैव सम डिफरेंट कलर. फाइन. लेट अस assume we have input A, we have PMOS, and we have NMOS, and we have output Y. Let us say input A is logic 0. तो इनपुट ए है लॉजिक 0, तो पीमॉस के गेट को गया 0, एनमॉस के गेट को गया 0। तो अगर गेट इज एट 0 ऑफ पीमॉस, तो पीमॉस क्या होगा? ऑन होगा। इफ 0 इज कनेक्टेड टू गेट टर्मिनल ऑफ द एनमॉस, एनमॉस रहेगा आपका ऑफ। सो इफेक्टिवली कैन आई से दैट, उसको स्विच डायग्राम में ड्रॉ करते हैं, पीमॉस इज ऑन, एनमॉस इज ओपन, ऑफ है ना। तो ये हो गया आपका VDD, यहाँ पे हो गया आपका Y। तो your Y is effectively connected to the VDD and it is disconnected from the ground. So Y is connected to VDD, therefore your output Y is equal to 1. On the same line, so if I say that the input A is now 1 volt, so one logic, so gate of the PMOS is 1 and NMOS का भी 1 है, so A is equal to 1, that is logic 1, so PMOS will be off, NMOS will be on, and effectively can I say that PMOS is now open circuited and now NMOS is on, so it is connected or shorted, so effectively our Y is connected to ground, so Y is equal to 0. So can I say that after analyzing this circuit from the given table and these two columns, अगर इनपुट A इक्वल टू 0 तो Y है आपका 1 और इनपुट अगर 1 है तो Y है आउटपुट आपका 0. It is going to act as an inverter. इतना समझ में आ गया? Yes or no?
Yes, sir.
Okay.
Yes, sir.
Okay, so we have analyzed our diagram, our schematic, and we have confirmed ourselves, okay, whatever schematic was given, it acts like a NOT gate, acts like an inverter. Third is Euler's diagram. Diagram ही लिखा था कि path लिखा था? हाँ, okay, Euler's path लिखा था. तो क्या करेंगे? इसमें बहुत स्ट्रेट फॉरवर्ड प्रोसीजर होती है. ऑब्जर्व, एक हॉरिजॉन्टल लाइन ड्रॉ की फॉर PMOS. ओके, then we do have another horizontal line for NMOS. Okay, how many inputs we do have? By looking at the equation, एक ही input है, so we will draw one input and we will name it as A. Okay, we will name it as A. मैंने ऐसे क्यों किया कि भाई यहाँ पे भी PMOS को भी गेट टर्मिनल है, NMOS को भी गेट टर्मिनल है, and this is A which is connected to the gate terminal of PMOS as well as gate terminal of the NMOS. तो ये हो गया आपका A as a gate terminal. Okay, now I want to have the connections. कैसे है? Now यहाँ पे बहुत ध्यान से देखिए, एक और चीज लिखने वाला हूं मैं. Can I have some different color? Okay, let's have the black. The terminal of PMOS which is connected to VDD is source and the remaining terminal automatically becomes drain. The terminal of NMOS which is connected to ground is source and remaining terminal automatically becomes drain. ये चीजें ध्यान रखनी है आपको. Okay, I repeat, the terminal of PMOS which is connected to VDD is source and the terminal of the NMOS which is connected to ground is source. Rest of the terminal you can definitely write down. Okay, so now looking at over here, the drain terminal of the PMOS and NMOS are shorted together and forming our output. Am I right? So we will have our output. Let us assume, okay, let us assume this is a drain and this is a drain. Okay, the side, this side, right hand side of the polysilicon is drain. What we have assumed. Okay, I repeat, this is assumed and both of them are shorted together. तो ये connection किया and this is going to be our output. Remaining terminals will be automatically become source. So source of PMOS is connected to VDD. Okay, connection दिखाओ, VDD लिखो. source of NMOS is connected to ground. Okay, line दिखाओ, connection दिखाओ, ground दिखाओ. So, oh my God, I am extremely sorry. I directly went for the stick diagram. um, I directly went for the stick diagram. Okay, fine. Extremely sorry. So this is called as the stick diagram. Okay, and in between, I will give you the Euler's path understanding. Okay, I am extremely sorry. Due to the practice of having the shortcuts, I directly went for the stick diagram. Okay, great, no problem. Okay, now in Euler's path, we are going to draw the NMOS and PMOS. Okay, तो कितने NMOS है अपने पास? एक ही NMOS है. Represent it as a single curve. Okay, कितने PMOS है? एक ही PMOS है. Represent it as a single curve. इस PMOS को इनपुट कौन सा है? A. इस NMOS को इनपुट कौन सा है? A. इस PMOS को इनपुट कौन सा है? A. ओके, सो फोर्थ पॉइंट, कॉमन पाथ. अभी फिलहाल तो वो कोई मायने नहीं रखता क्योंकि एक ही इनपुट है, बट फॉर द सेक ऑफ प्रोसीजर ओनली. ओके, तो इस पॉइंट से इस पॉइंट तक वी कैन गो थ्रू A. Similarly, from this point to this point, we can go through A. So we can have the common path A. Okay, and therefore we have A. फिलहाल के लिए for inverter, the procedure number 3 and 4, step number 3 and 4 doesn't make any sense. But as soon as your number of input becomes more, okay, 3, 4, 5, this becomes very, very important. So for the sake of procedure only, step number 3 and step number 4, we have written over here. We are trying to find the common path to go from this point to this point and this point to this point. So common path is A. Did you understand point number 1, point number 2, then point number 3 over here, point number 4, and this is point number 5, stick diagram. Okay. Euler's path में क्या किया? We have represented each and every MOSFET with a curve. NMOS एक ही था तो एक ही कर्व आया, PMOS अगर एक है तो एक ही कर्व आया. इन दोनों के गेट को जो इनपुट नाम है, यहाँ पे क्या है? A है, इसलिए यहाँ पे A लिखा और यहाँ पे भी A लिखा. Okay, we will understand the Euler's path in more detail whenever we will have the more number of inputs. But till this stick diagram, did you understand? Yes or no?
Yes, sir.
Okay, great. Okay, one student, yes, that's my success. One student said yes. And the next one is layout. Okay, तो ये stick diagram बनाने के बाद the rest is just drawing the rangoli. We always call it as rangoli. Okay, why? You will come to know. Now let me go and open up the Microwind. Okay, so we do have a Microwind software. This is Microwind 3.1, and can you see something black over here? Yes or no? Some sort of palette with lots of colors into it. Can you see?
Yes, sir.
Okay, great. I want to concentrate or zoom in to video at the bottom of your Microwind. यहाँ पे कुछ CMOS 90 nanometer 6 metal copper strand SIGE low K 1.2 volt 2.5 volt ऐसे कुछ लिखा है. You can zoom into video and you can read that line. Have you gone through the words written over there? So we do have CMOS 90 nanometer technology. Now you do understand 90 nanometer technology. 6 metal means we are going to use 6 different metals. We can use them. Okay, those metals are starting from copper and strained SIGE. Low K material we are using for the wafer. And we can use 1.2 volt as a usual VDD supply and 2.5 volt as a high VDD supply. Okay, very interesting thing is going over here. Can you see the dots, yellow dots over here? Yes.
Yes, sir.
Okay, great. So I have increased the distance between the yellow dots and I want you to concentrate on the left hand side top corner. वहां पे कुछ लिखा है 1 lambda is equal to 0.050 micrometer. Very important thing. अगर एग्जाम के लिए बोलो तो वाइवा के लिए बहुत ज्यादा इंपॉर्टेंट है. ओके क्या लिखा है वहां पे? लेट मी राइट इट डाउन. 1 lambda is equal to 0.050 micrometer, or I will say that 2 lambda is equal to 0.1 micrometer, or I can say that 100 nanometer, or which can be nearly equal to 90 nanometer. So 90 nanometer refers to the technology, okay, and that refers to the channel length. So I can say that a universal formula channel length is always equal to 2 lambda. And here your industry plays a very important role. This lambda, okay, your all the designs are going to come over here in terms of lambda. Channel length kitna hai? 2 lambda. Width kitna hai? 8 lambda, and so on. They never talk about the nanometer and the micrometer. No. Okay. So once you fix your technology, you always talk about the lambda. Okay. आपको वो पता भी चलेगा. Now inside this palette, if your palette is not visible, you can get it from here. Okay. अगर यहाँ पे आप click करते हो तो you will have palette, and in this palette you do have some MOSFET generator. Okay. So we can generate NMOS and PMOS, and now you can look into this diagram. दिख रहा है आपको? L भी दिख रहा है, W भी दिख रहा है. जो discussion हमने किया, exactly same discussion is available. The exactly same discussion or theory the software is using at the backend. The length of the MOSFET and the width of the MOSFET. So width of the MOSFET right now it is 0.5 micrometer and length is 100 micrometer, that is 100 nanometer, nearly equal to 90 nanometer. You can click on the generate device, okay, and you can place it. Let me zoom out a little. ये है NMOS. Do it look like a top view of NMOS we discussed about? कि भाई एक red color की strip है जो polysilicon है. On the either side of the polysilicon strip we will have N plus diffusion. Let me delete some part of the layout. इसको क्या कहते हैं? Layout. ये यहाँ पे gun है. इसके ऊपर क्लिक कीजिए. You can click on the part of the layout. तो मैं इस blue region पे click करने वाला हूँ. It vanishes. Okay. So this green color you can see over here. I will take and draw a rectangle by dragging the cursor. This is N plus diffusion. Okay. Then metal 1, I will draw another rectangle by dragging the cursor. This is metal 1, blue one, and the rectangles with the cross are the connection contacts. Okay. So polysilicon hai, on the either side we do have N plus diffusion. We do have metal और N plus diffusion को connect करने के लिए आपने contacts भी रखे हैं. Okay. Let me try something different as well. Okay. Let us not discuss this one. It will require a much more discussion in the detail. Fine. So this looks like the top view which we discussed in the starting of the session. Okay. जो भी हमने discuss किया वही software use कर रहा है. So this NMOS looks like the discussion, and let us now go for the PMOS. Let us now generate it. It once again looks like the same way we discussed. Polysilicon, ये brown region है कुछ, so that is your P plus diffusion. Okay. The blue strips are the metal and the white rectangles are your contacts, and the green dotted region surrounding your PMOS is your N-well. You do have N-well over here. Okay. Let me draw that N-well. Okay. So you do have everything in the practical approach compared to the theoretical approach. तो MOSFET में जो theory में पढ़ने वाले हो वही practical में करने वाले हो. Okay, so what now we are going to do? We are going to have our MOSFET design. Okay, for an inverter we will require one NMOS and we will require one PMOS. Let us put them together. Okay, now going back to our slide, you can see over here. Okay, ये स्टिक डायग्राम जो निकाली थी, सॉरी, स्टिक डायग्राम में क्या है, एक वर्टिकल पॉलीसिलिकॉन दिख रहा है, am I right? We will try to have the same polysilicon over here. Now इसमें ना मैं थोड़ा सा जूम करके दिखाता हूं. यहाँ पे एक ऑप्शन है आपको मेनू में, एक कॉपी का ऑप्शन है और यहाँ पे अगर देखोगे तो इट सेज मूव एंड स्ट्रेच. ओके, तो इसके ऑप्शन दिख रहा है आपको. तो ये जो ऑप्शन है, इफ आई क्लिक ऑन दिस लाइन, तो मैं इसको स्ट्रेच कर रहा हूं. कैन यू सी द डॉटेड लाइन? कैन यू सी द डॉटेड लाइन? I want to make sure that you can see. Okay.
Yes, sir.
Yes,
Okay,
sir.
great. Okay, great. So I am moving my hand right now. Okay. So you can stretch one side of any rectangle. For us, all of them
Sir.
are rectangle. Yes, yes.
So
Yes.
from where we have to select PMOS and NMOS?
Okay. In this palette, you do have one option over here, MOS generator. ये जो option है, I really can't zoom into it, but यहाँ पे एक option है MOS generator का. अगर इसके ऊपर आप क्लिक करते हो तो आप ये palette आता है, ये window आता है. From here you can choose either NMOS or PMOS, NMOS or PMOS, and you can click on the generate device. फिलहाल तो कुछ नहीं दिखेगा, and once you click somewhere तो आपका device appear हो जाएगा. Okay, you can erase the layout. Okay. Now there is a Viva question, very interesting and tricky Viva question. Looking at the layout of PMOS and NMOS, can you tell me the black region is dash dash type of material? Black region is your wafer. On the wafer we are fabricating NMOS and PMOS, and looking at the layout of the NMOS and PMOS, the wafer material is dash dash type material, semiconductor material. And the answer is okay. The answer कहाँ पे गया हाँ, N MOSFET तो हाँ P type, yes. N MOS तो वैसे है और P MOS को बनाने के लिए N well लग रही है. So definitely our substrate is of P type material. So this black region which is substrate, which is wafer, is a P type wafer. Okay. So now let us once again stretch our polysilicon and let us connect it together. Okay, it looks like our stick diagram. एक बना लिया, am I right? Okay. So ये पॉलीसिलिकॉन बन गया. Okay. तो अभी कैसे मैं sentences को कैसे बदल रहा हूँ? Now right hand side of the polysilicon are shorted together. Fine. Go to the layout. Once again stretch. Right hand side of the polysilicon are shorted together. Go back to stick diagram. Left hand side terminal of PMOS is connected to VDD. Okay. Left hand side terminal is connected to VDD. यहाँ पे ये जो ब्लू कलर दिख रहा है ना, ये है आपका VDD पावर सप्लाई. फिर से स्टिक डायग्राम में गए, लेफ्ट हैंड साइड ऑफ द NMOS इज कनेक्टेड टू ग्राउंड. लेआउट में जाओ, आपके पास ग्राउंड है, पिकअप करो एंड प्लेस इट ओवर हियर. दिस N well has to be polarized, so we need to put a VDD supply inside the N well. Okay, क्योंकि that is a body terminal. Okay, do remember that. Another important point, body terminal of PMOS is always connected to VDD and body terminal of NMOS is always connected to ground, so that the diffusions are well isolated from the substrate. ये जो diffusions है आपके N plus and N plus P plus and P plus, तो यहाँ पे आपका depletion region अच्छे से बने, इसके लिए we do polarize body terminal of PMOS, that is N well, it is connected to VDD, and body terminal of PMOS, that is your substrate, it is connected to ground. Okay. एक टॉपिक भी है आपको वाइवा में पूछा जाता है, बॉडी थ्रेशोल्ड वोल्टेज करके. तो थ्रेशोल्ड वोल्टेज में प्रॉब्लम आते हैं, तो यू नीड टू रीड अबाउट इट। ओके, तो ये समझ में आ गया। वंस अगेन गो बैक टू स्टिक डायग्राम। जो शॉर्ट किया था वहां पे क्या है, आपका आउटपुट है। गो बैक नाउ इनटू पैलेट, यू डू हैव एन आई, जस्ट क्लिक ऑन इट, hover your mouse, ड्रैग नहीं करना है, लेके जाना है सिर्फ, एंड यू कैन वंस अगेन क्लिक ऑन द मेटल। तो यहाँ पे आपको दिखेगा कि भाई यहाँ पे डीसी सप्लाई भी है, क्लॉक भी है, मींस यू कैन अप्लाई द क्लॉक, यू कैन अप्लाई द पल्स, यू कैन अप्लाई द साइनोसाइडल, you can have the variable, your outputs are always variable. Okay, rest of the things were sources. Okay, तो यहाँ पे मैं नाम दे देता हूँ इसको y, assign. Okay, input कहाँ पे है, input is your polysilicon, the red line A. तो क्या करेंगे, वही I लेंगे और A पे रखेंगे, सॉरी पॉलीसिलिकॉन पे रखेंगे, उसको नाम देंगे A, and we want to apply the clock. We will choose the clock. उसका लेवल 1 क्या है, 1.2 वोल्ट, लेवल 0 क्या है, 0 वोल्ट। You have your timings, okay, high time and low time. You can make your clock slower, click on it, or you can make your clock faster. Okay, so click on assign, you will have A over here. So we have applied the input as well as we have applied the output. One important thing, we need to check for the DRC, design rule check. If you are clicking on this option, design rule check, it is going to check for the dimension rules of your layout. अभी मैं क्लिक कर रहा हूं लेकिन कुछ एरर नहीं आ रहा है. Let me introduce some error. Okay, I will move these sources a little higher, and I will also move this one a little higher. Okay, let me reduce the polysilicon a little. Okay, ये unnecessary metal भी कम कर देता हूं. Now let me click on the DRC. What it says, the letters are very tiny. You can zoom in into your video. The letter says, the error says, the 4 lambda between anvil and diffusion n is less than 6 lambda, rule number 204. Arre baap re, rule number 204. And you do have literally you do have thousands of rules. Okay, out of those thousands of rules, you have rule number 204. It says that कि भाई जो anvil है और जो n plus diffusion है, इनके बीच में फिलहाल जो 4 lambda distance है ना, वो 6 lambda से कम है. So software requires that distance to be at least 6 lambda. And how we come to know 1 lambda? The distance between two dots over here is 1 lambda. So 4, it is 5, it is 6. Okay, now I need to handle the polysilicon layers as well. Okay, now let us once again click on DRC. Okay, fine, we have removed the error. Now we are ready to simulate it. Okay, let us see. This is a simulation button. Click on it. Can you see the green lines and the red lines? Whenever green is 1, then red is 0. Whenever green is 0, red is 1, and so on. Okay, so green one is A and red lines are Y. So your design is acting as inverter. Now what we need to do, when you are going to prepare your manual, what you need to have, let me show it to you. First point, remember, press F5, it will toggle your mode. Okay, F5. अगर F5 ध्यान में नहीं रहा तो यहां से आप कर सकते हो कलर्स, स्विच टू मोनोक्रोम, कलर्स, स्विच टू कलर, स्विच टू मोनोक्रोम निकालना पड़ेगा, व्हाइट बैकग्राउंड, ओके, स्विच टू कलर एंड सो ऑन. ओके, तो ऐसे बना के स्विच टू मोनोक्रोम, दैट इज F5. प्रिंट स्क्रीन कीजिए, आपके वर्ड डॉक्यूमेंट में जाइए, यहाँ पे पेस्ट कीजिए and crop the unnecessary part. Okay, तो ये बन गया आपका, क्या बना, लेआउट. बाद में सिमुलेट कीजिए. ओके, अभी मैंने मैक्सिमाइज किया तो मेरी वैल्यूज यहाँ की चली गई. आई विल रिसेट इट. यू कैन सी 3 पिकोसेकंड, 3 पिकोसेकंड, 3 पिकोसेकंड समथिंग. दोज आर राइज टाइम एंड फॉल टाइम. वंस अगेन प्रिंट स्क्रीन कीजिए एंड पेस्ट योर डिजाइन. रिमूव अननेसेसरी पार्ट. Okay. Actually, this the above part is your layout, and next is simulation without. Very interesting thing is going to happen over here now. लोड कैपेसिटर. देखो इन्वर्टर तो हमेशा कभी अकेले काम नहीं करेगा. You will have your pins associated with it, next logic or some sort of design associated with the inverter. तो अकेला इन्वर्टर तो कुछ काम नहीं करता. उसका लोड so capacitance into it. Let me switch back to color. Okay, now in the palette you do have this capacitor. Click on it, place it on your design. It will ask you to put the value. Let our capacitor to be 0.01 picofarad, a very small capacitor. Okay, and let us once again simulate it. Can you see now your 5 picosecond? Not 5, the 3 picosecond value. Okay, previously it was 3 picosecond, the rise time and the fall time. Okay, those were only 3 picosecond, and due to addition of the load capacitance, those got rise time is equal to 21 picosecond and fall time equal to 12 picosecond due to addition of a small capacitor. Okay, 0.01 picofarad. तो इसका screenshot लोगे आप and you have to put it over here. Okay, remove the unnecessary part of your screenshot. We don't want it into the printout. Okay. With load capacitor. और लोड कैपेसिटर कितना रखा है 0.01 पिको फैराड. तो ये बना आपका इन्वर्टर का एक्सपेरिमेंट. समझ में आ गया आपको? तो लेआउट रहेगा आपका, बाद में सिमुलेशन विदाउट लोड कैपेसिटर और बाद में सिमुलेशन विथ लोड कैपेसिटर. जैसे इन्वर्टर के लिए किया वैसे ही सेम चीज आप करोगे NAND, NOR, half adder, full adder and so on. Okay, इतना इन्वर्टर का समझ में आ गया सबको? Yes or no?
Yes, sir.
Okay, great.
Yes, sir.
Okay.
Yes, sir.
सर मेटल पे कैपेसिटर ऐड करना है ना?
हाँ जी, हाँ जी. ये जो कैपेसिटर यहाँ पे रखा था, यू कैन मूव दिस कैपेसिटर. ओके, ये जो मेटल है इसके ऊपर सिर्फ आपको ड्रैग एंड ड्रॉप करना है आपके कैपेसिटर को. यहाँ से उठा के जस्ट प्लेस करना है बस, बाकी कुछ नहीं. ओके, इन्वर्टर समझ में आ गया सबको? नाउ व्हाट वी विल डू only one more design, that is your NAND design, and we will go with our procedure, and that will be the last design which we are going to do manually. Later I will show you the demonstrations. Okay, now we want to have the NAND gate design. First, Boolean equation y is equal to ab bar. Second, schematic. अभी यहाँ पे एक नया टेबल देने वाला हूं मैं, NMOS, PMOS. Oh, sorry, not series. Okay. अगर एडिशन रहा या फिर मल्टीप्लिकेशन रहा तो क्या होने वाला है? हाउ टू यूज दैट टेबल वी विल सी. अगर एडिशन रहा तो NMOSes will be connected in parallel, whereas PMOS will be connected in series, whereas multiplication रहा तो NMOSes will be connected in series, whereas PMOSes will be connected in parallel. इसका मीनिंग क्या हुआ? ये सेकंड टेबल है, वेरी इंपॉर्टेंट टेबल. इसका मीनिंग क्या हुआ? ये जो इक्वेशन है इसमें क्या है? मल्टीप्लीकेशन है. a डॉट बी उसका कॉम्प्लीमेंट है बाद में. ओके, a डॉट बी. सो सेकंड पार्ट जो है उसका स्कीमेटिक बनाना है. सो वी डू हैव अ मल्टीप्लीकेशन. So PMOSes will be connected in parallel and NMOSes will be connected in series, and we do have two inputs A and B. So look over here how we are going to draw. PMOSes are going to connect in parallel. Okay, तो भाई दो PMOS ले लो आप, दोनों को आप पैरेलल में कनेक्ट कर लीजिए। तो ये बन गया VDD, ये बन गया एक इनपुट, ये एक दूसरा बन गया दूसरा इनपुट, ये आपका आ गया आउटपुट। ओके, बाद में NMOSes has to be connected in सीरीज। ओके, सो दो NMOSes को आप सीरीज में कनेक्ट कर दीजिए। ए इनपुट बी इनपुट, ये बना VSS मतलब ग्राउंड, और इसको लेके गए आउटपुट में। ओके, तो स्कीमेटिक बन गया। स्कीमेटिक में क्या मेंशन करने वाले हैं, और एक चीज उनके सोर्स एंड ड्रेन। तो ए पी मॉस का ये बना सोर्स, ये बना सोर्स, ये बना ड्रेन, ये बना ड्रेन। ओके, whichever terminal of the NMOS is connected to ground, it is source. Remaining terminal becomes automatically drain. ये जो टर्मिनल है NMOS with input A, it is going towards the ground, so therefore it becomes source and remaining terminal becomes drain. ये schematic की चीजें हो गई। Next point is, next step is Euler's path. इसमें क्या करते हैं कि भाई एक हॉरिजॉन्टल, सॉरी आपका जो NMOS है, फिर से मैं जाने वाला था स्टिक डायग्राम में, NMOS और PMOS, ओके, इनको ड्रॉ करते हैं, देखते हैं अभी कैसे होगा। नाउ वी डू हैव, लुक एट द PMOS बैंक, लेट मी ड्रॉ अ रेक्टेंगल ओवर देयर। ये है आपकी PMOS बैंक और ये है आपकी NMOS बैंक, एम आई राइट? PMOS बैंक एंड NMOS बैंक। तो NMOS अगर देखोगे तो वी हैव one NMOS and two NMOS. Both of them have input A and B respectively. And we do have another bank, that is PMOS bank. And for that, we do have two parallel connected MOSFETs. So one is A MOSFET and another is B MOSFET. Okay, both of them are connected together. फॉर एन एग्जाम्पल, अगर फॉर एन एग्जाम्पल, सिर्फ एक एग्जाम्पल के लिए थोड़ा सा बता देता हूं मैं, थोड़ा सा नैन को बाजू में रखते हैं। इफ वी डू हैव अ काइंड ऑफ डिजाइन लाइक दिस, स्कीमेटिक लाइक दिस, okay, all of them are PMOSes. तो इसका यूलर्स पाथ आप कैसे ड्रॉ करोगे? लेट अस से A B C D, तो A B A B, ओके, यहाँ पे शॉर्ट है, am I right? तो यहां से निकला C। देखिए यहाँ पे और यहाँ पे कनेक्शन नहीं है, ये C डायरेक्टली कनेक्टेड है D को और D बाद में B को, तो यहाँ पे कनेक्शन नहीं है। अगर अगर आपके स्कीमेटिक में फॉर सम रीजन यहाँ पे कनेक्शन होता, अगर होता, तो ये भी यहाँ पे कनेक्टेड होता। गॉट इट? तो हैव अ हैबिट और प्रैक्टिस ऑफ ड्राइंग द यूलर्स पाथ। आजा भाई, कलर चेंज हो जा। ओके, नाउ फोर्थ इज कॉमन पाथ। तो वी कैन स्टार्ट फ्रॉम दिस पॉइंट एंड गो टू दिस पॉइंट as A B, or we can go by B A. Similarly in PMOS, from this point to this point we can go by A B or B A. We can complete our path. So you can choose either go for A B or B A. Both of them are valid path. Now how to use them? That is in stick diagram. Okay, that is in stick diagram. So what happens in stick diagram? Let us draw one horizontal line for PMOS. Okay, fine. And one horizontal line for NMOS. I want to show you both designs. Okay, this is your PMOS. First option, if we choose AB as a common path. Okay, so we will, how many inputs we do have? Two inputs. So two vertical lines and its name will be AB. अगर आपने ये पाथ चूज किया which is perfectly fine, तो आप नाम दोगे BA. Okay, it is up to you which path you choose. There can be multiple common paths, so it all goes up to you कि भाई आप क्या चूज करने वाले हो. So we have chosen AB as a path. Now look at the schematic. The source, now we are talking about PMOS. Okay, I repeat, we are talking about PMOS bank. The source of A is connected to source of B. Do remember that in your stick diagram, this side and this side are by default shorted. This side and this side are by default shorted. So looking at the schematic for PMOS bank, source of A and source of B are shorted together. Okay, so we will assume this to be source and these both sources are going to VDD. Okay, so this is VDD. Automatically remaining terminal became drain. Now going to NMOS bank. Okay, before going to NMOS bank, we will finish the PMOS bank. The drain of A and the drain of B are once again shorted together. Okay, we are talking about the PMOS bank. So drain of A and drain of B are shorted together. देखो ये जो A है A polysilicon का drain और ये जो B है B polysilicon का drain are shorted together and are actually forming to the output, are going to the output. Okay, now we will go to the NMOS bank. Look here, this terminal and this terminal are shorted. Now which two terminal of both NMOSes are connected together? Source terminal of A NMOS and drain terminal of B NMOS. Source terminal of A NMOS and drain terminal of B NMOS are connected together. Remaining terminal automatically become drain and this becomes source. Drain of A is connected to output. Drain of A is connected to output and source of B is connected to ground. Source of B is connected to ground. Have you understood this diagram? Yes, sir.
Yes, sir.
Okay, great. Now, after understanding this diagram, let me exit my slideshow and let us go back to Microwind. I will go for new layout. I don't want to save the previous layout. Okay, fine. Now, how many MOSFETs we require? 2 PMOS and 2 NMOS. Am I right? Let us get them. Oh, sorry. So we will require NMOS. We will require 1 PMOS. And looking at the stick diagram, as usual, we align their polysilicon, the red line. We align their polysilicon. So shift your PMOS a little and let us short their polysilicon together. So we do have this 1 NMOS and 1 PMOS and let us copy it. So we do have 2 PMOS and 2 NMOS. और जैसे स्टिक डायग्राम में होने वाला है कि दोनों के पॉलीसिलिकॉन एक दूसरे से कनेक्टेड है तो वैसे होने वाले हैं. नाउ यू डू हैव अ चॉइस. पे अटेंशन. ओके, देखो स्टिक डायग्राम में देखो यहाँ पे. कैन आई जूम इन? यस. ओके, तो ये जो पॉलीसिलिकॉन है वर्टिकल लाइन ये एक दूसरे से कनेक्टेड है. जैसे मैंने कहा था कि भाई दिस साइड एंड दिस साइड आर शॉर्टेड टुगेदर बाय डिफॉल्ट. तो मेरे पास ऑप्शन है कि भाई मेटल को लीजिए एंड यू कैन सिंपली कनेक्ट इट टुगेदर. ओके, ऐसे कर सकते हो आप, कोई दिक्कत नहीं. ओके, एंड वंस अगेन यू कैन ड्रॉ अ मेटल रेक्टेंगल ऑन दिस साइड, द NMOS side. But what conclusion I want to make it over here is interesting conclusion. देखिए ये कॉन्टैक्ट, ये टर्मिनल और ये टर्मिनल एक दूसरे से शॉर्टेड है, मीन्स व्हाट, दे आर फॉर्मिंग सिंगल इलेक्ट्रिकल नोड, एम आई राइट, दे आर फॉर्मिंग सिंगल इलेक्ट्रिकल नोड। अगर मैं ऐसे कनेक्शन करूं तो भी कोई दिक्कत नहीं है, एंड सिंस दोज आर कनेक्टेड टुगेदर, दोज आर शॉर्टेड टुगेदर, आई कैन हैव one interesting thing over here. I will do undo. In Microwind you can do undo only once, very important, undo एक ही बार होगा क्योंकि this is VLSI, कोई खेलते नहीं बैठता। If you go for once again in the edit menu you can see undo is disabled, you can undo only once। अगर लाइसेंस वर्जन रहा तो आप बहुत बार कर सकते हो। ठीक है। Now since this contact is going to be connected this with this contact, and those are forming the single electrical node and both the contacts are shorted together, so let the both contacts short together। तो उनको कर दिया शॉर्ट, तो क्या फायदा हुआ आपका, आपका लेआउट का एरिया कम हो गया। लेआउट का एरिया कम हो गया मतलब आपके वेफर पे और ज्यादा डिजाइन आप इनकॉर्पोरेट कर सकते हो। नाउ दिस लुक्स लाइक आवर स्टिक डायग्राम, टू वर्टिकल लाइंस, टू रेड कलर वर्टिकल लाइंस, ऊपर में है पीमॉस बैंक, ओके ऊपर में है पीमॉस बैंक, नीचे में है एनमॉस बैंक, ओके नीचे में है एनमॉस बैंक। नाउ वी विल चेंज आवर सेंटेंसेस, कैसे कि दो पॉलीसिलिकॉन के बीच में जो टर्मिनल है इट इज गोइंग टू द VDD इन PMOS। ओके दो पॉलीसिलिकॉन के बीच में जो भी टर्मिनल है it is connected to VDD and we will reduce the extra metal। okay, the either side are connected to each other, एक दूसरे से कनेक्टेड है, फाइन। चलो तो मैं उनको नीचे से कनेक्ट कर लेता हूँ, सॉरी बहुत ज्यादा कर लिया। मेटल 1 को लेते हैं एंड वी विल ड्रॉ अ रेक्टेंगल, तो हमने उसको नीचे से कनेक्ट कर लिया, जैसे स्टिक डायग्राम में दिख रहा है वैसे ही किया, am I right? अभी आते हैं एनमॉस में। एनमॉस में यहाँ पे जो कनेक्शन है वो कहीं पे जा रहा है क्या, इट इज कनेक्टेड नोवेयर, इट इज गोइंग नोवेयर, तो एक्स्ट्रा मेटल जो है उसको रिड्यूस कर देते हैं, फंटास्टिक। ओके नाउ दिस साइड ऑफ द B polysilicon is connected to ground, okay this side is connected to ground, तो मेटल को थोड़ा सा कम करते हैं और इसको यहाँ पे स्ट्रेच करके ग्राउंड अटैच कर देते हैं। दिस साइड इज कनेक्टेड टू द आउटपुट, ओके फाइन, तो नीचे से कम कर लेते हैं, ऊपर में स्ट्रेच करके उसको कनेक्ट कर लेते हैं। एंड वन मोर इंपॉर्टेंट थिंग, पोलराइज योर एनवेल, अप्लाई VDD टू एनवेल, दैट इज योर बॉडी टर्मिनल ऑफ, क्या कहते हैं उसको, PMOS। नेक्स्ट, this left hand side polysilicon is input A, fine, pick up your eye, place it on the polysilicon, give it a name A, apply a clock, observe the timing, okay, यहाँ पे टाइमिंग देखिए अभी फिलहाल क्या है, ये 0.09 नैनोसेकंड, इसको असाइन किया। मैंने अगला आई लिया, अगले पॉलीसिलिकॉन पे लिखा रखा, and now you can observe the tool has automatically updated the timing। पिछला क्या था, 0.09 था, अभी यहाँ पे क्या आ गया, ऑटोमेटिकली 0.19 नैनोसेकंड। इसको असाइन कर लिया, उप्स मैंने नाम नहीं चेंज किया, इसको डबल क्लिक करते हैं और इसको नाम चेंज कर देते हैं B। ओके देन आई विल टेक द विजिबल नोड वंस अगेन एंड आई विल प्लेस इट ओवर हियर, वी विल नेम इट एज Y and it has to be variable, outputs are always variable, assign। तो मैंने जैसे स्टिक डायग्राम बनाई थी वैसे देखे देखे देखते 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 मैंने लेआउट भी बना दिया। नाउ इट्स टाइम फॉर DRC, डिजाइन रूल चेक। क्या है, द स्पेसिंग बिटवीन मेटल इज लेस देन 4 लैम्डा। भाई अभी यहाँ पे जो मेटल दिख रहा है इट्स स्पेसिंग इज लेस देन 4 लैम्डा, तो 1 लैम्डा से कम कर देते हैं और नीचे से 1 लैम्डा बढ़ा देते हैं। लेट अस गो फॉर DRC वंस अगेन। ओके तो क्लिक भी करूँ तो कुछ पॉपअप नहीं आ रहा है, मीन्स आवर डिजाइन रूल चेक इज ओके। DRC चेक्स फॉर द physical dimension, geometrical dimensions of your design। Now let us go for simulating our design। बहुत सारी vertical lines है, those are due to the delay, मैं उनको रिमूव करता हूँ, एक टाइम स्केल भी थोड़ा छोटा रखता हूँ, रिसेट करते हैं। ओके सो NAND गेट इंप्लीमेंट किया है, राइट। NAND गेट का प्रॉपर्टी अगर देखोगे आप तो क्या आएगा? If both the inputs are 1, then and then only output is 0, otherwise output is 1. तो जब भी दोनों भी इनपुट 1 होंगे तभी आपका आउटपुट इज 0, अदरवाइज अवर आउटपुट रिमेन्स 1. दोनों भी इनपुट जब 1 है तब आउटपुट आपका 0 हो रहा है. ओके, so you can now see the delay. Click on the delay and reset your simulation. You can see, okay, rise time is something 2 picosecond and fall time is also 2 picosecond, and it goes on improvising. Now next part is go to the palette, pick up your क्या कहते हैं उसको, load capacitor. Okay, once again simulate your design, DRC, and now you can see what is the problem with the solution simulation. Let me remove the delays and reset the design. बहुत सारे कर्व्स आ रहे हैं अभी. That is the biggest problem with our digital designs, the load capacitor. जब भी वो आ जाता है ना तो आपका simulation result है ना वो बर्बाद होने वाला है. So that's why we do device sizing. एक theoretical part है आपके VLSI में device sizing के, devices को बड़ा करो, छोटा करो, and so on. It was a part of practical in the year of 2010 and 2011, but now it is not part of practical for your curriculum. But you can observe the sluggishness, the increase in rise time and the fall time due to addition of the load capacitance. Okay, तो आपका fall time आ रहा है फिलहाल 21 picosecond and rise time आ रहा है 11 picosecond. You have to prepare your manual in the same way. जैसे मैंने पहले कहा था, ब्लैक एंड व्हाइट लेआउट, ब्लैक एंड व्हाइट सिमुलेशन विदाउट लोड कैपेसिटेंस, ब्लैक एंड व्हाइट सिमुलेशन विद लोड कैपेसिटेंस. तो ये आपको करना है. डिड यू अंडरस्टैंड द NAND गेट? यस और नो?
सर कैपेसिटर पैलेट से ऐड करना है ना?
यस यस, पैलेट में आपके पास ऑप्शन है कैपेसिटर का, उसको पिक करके आपको सिर्फ आउटपुट जो लाइन है ना वहां पे प्लेस करनी है. ओके, एनीथिंग एल्स? एनीथिंग एल्स? Can we ask someone?
Sir, can you explain stick diagram again?
Stick diagram?
फिर से explain करो ना.
Okay, fine. So we will go back to PPT and let us start the slideshow. Stick diagram. तो अभी क्या करते हैं, पिछली बार AB लिया था ना, तो इस बार BA लेते हैं. मतलब we want to use this common path. Is it okay?
Yes, sir.
Okay. So by procedure, one horizontal line for PMOS and another horizontal line for NMOS. Okay, great. Now we do have two inputs, therefore we will have two vertical lines which are going to be our inputs. Now the sequence for them we are going to take as BA. Okay, पिछली बार क्या लिया था, AB लिया था, इस बार BA ले रहे हैं. Okay, now we will have this schematic. Okay, by default this side and this side are shorted together. So for PMOSes, let us consider once again, source and source are shorted together and those are connected to VDD. Automatically this becomes drain and this becomes drain. The drain of A and B P MOSFETs are shorted together. Okay, fine. Both of them are shorted together. Great. And those are going to form our output. Okay, drain से जो भी टर्मिनल निकल रहा है ये कहाँ पे जा रहा है, आउटपुट को जा रहा है. We are looking at the schematic, and after looking at the schematic we are drawing the stick diagram. Okay, the sequence of polysilicon is taken from step number 3 and step number 4. Sequence of polysilicon. Now come to NMOS. This side and this side of NMOSes are connected to each other by default. So source of A and drain of B. source of A and a drain of B are shorted together. देखो यहाँ पे change हो गया. Okay, and remaining terminal will be automatically, this will be source and this will be drain. So drain of A is going to output. Okay, drain of A is going to output. Great. And source of B, the source terminal of B is going to ground. Source of B is going to ground. तो मैंने अगर सीक्वेंस थोड़ा सा अलग लिया तो मेरा स्टिक डायग्राम भी चेंज हो गया. Did you understand?
Yes, sir.
Okay, great. So we do have stick diagram. तो उसके हिसाब से आपका लेआउट भी चेंज होगा. Okay, so we have to make some changes into the layout by looking into the stick diagram. तो इन्वर्टर और नैंड एक बार बहुत अच्छे से समझ में आ गए. Now you are expert. Okay, what you need to do? You need to do practice for drawing the layout. It requires practice. Since I am drawing the layout since last almost 7 years on Microwind, I am much more habitual for that. Whenever you are going to draw, you are going to do mistakes. You will have DRC errors. Okay. So you have to do practice. And now after discussing NAND and inverter, that is NOT gate in detail, now we are going to become some instrumental. Now I will show you the demonstration, a little bit demonstrations and a Word document. Okay, and we will see how it can be done. So I will go to new and I will not save my layout, and let me show you the Word document which I do have with me. Okay, can you see this document? Let me zoom in a little. Can you see the Word document?
Yes, sir.
Great. तो ये इन्वर्टर पढ़ा था थोड़ी देर पहले, am I right? तो इन्वर्टर का डायग्राम, यूलर्स पाथ, कॉमन पाथ जो है, स्टिक डायग्राम ड्रॉ की और स्टिक डायग्राम से लेआउट ड्रॉ किया. यही देखा था इन्वर्टर के लिए. ओके, नाउ वी विल गो टू, दिस इज NAND गेट. ओके, दो PMOS कनेक्टेड टुगेदर, NMOS is कनेक्टेड इन सीरीज. तो आपका PMOS और NMOS का यूलर्स पाथ बना, उसके ऊपर से स्टिक डायग्राम बनाई. स्टिक डायग्राम आपको समझ में आ गई. ओके, to prepare the schematic we will require the understanding, not really understanding but memorization of the this table. NMOS and PMOS पैरेलल और सीरीज में कब कनेक्ट करेंगे, ये बहुत जरूरी है. ओके, ठीक है, स्कीमेटिक बनाने के लिए इस टेबल की जरूरत आपको पड़ने वाली है. देन आफ्टर लुकिंग एट NAND गेट ऑन द सेम लाइन वी डू हैव NOR गेट. NOR गेट का इक्वेशन क्या बनेगा आपका, A plus B. Am I right? Let us go back to PPT. NOR गेट क्या रहेगा, y is equal to a plus b बार. और पता है कि भाई अगर प्लस है तो NMOS पैरेलल में कनेक्ट होंगे और PMOS सीरीज में कनेक्ट होंगे. मतलब PMOSes has to be connected in series. Inputs are A and B, whereas NMOSes has to be connected in parallel. A and B, it is connected to ground, it is connected to VDD, और यहां से दोनों के बीच में से जो कॉमन निकलेगा इट इज योर आउटपुट. तो यही स्कीमेटिक यहाँ पे ड्रॉ किया है. PMOSes are connected in series, NMOSes are connected in parallel. सोर्स एंड ड्रेन नॉमेनक्लेचर निकाला, यूलर्स पाथ आइडेंटिफाई किया, कॉमन पाथ, अभी 2 ही टर्मिनल है तो फिर इजी है। एंड यू हैव ड्रॉन द स्टिक डायग्राम, स्टिक डायग्राम से आपको लेआउट ड्रॉ करना है। ओके, नाउ इट कम्स टू हाफ एडर। You do have an equation sum is equal to a x or b, और जैसे मैंने कहा था कि डबल कॉम्प्लीमेंट लेना पड़ता है आपको, so accordingly you will have the equation for sum as well as equation for carry। तो यहाँ पे देखिए अभी सम के इक्वेशन में अगर आप देखोगे तो a बार b बार प्लस a b और होल कॉम्प्लीमेंट, so we have treated a bar b bar a b as 4 different inputs, you can see over here in the diagram, a bar b bar a b and so on। Okay, and in the NMOS you can also have a b a bar b bar, so you do have a sum logic and a carry logic। after looking at the equations को सही सही बना लीजिए, इक्वेशन बनने के बाद इस टेबल को रेफर कीजिए। ओके, इस टेबल को रेफर कीजिए, टेबल को रेफर करके ये स्कीमेटिक बनेगा, स्कीमेटिक बनने के बाद आपके यूलर्स डायग्राम बनेंगे। ओके, PMOS एंड NMOS का फॉर सम लॉजिक एंड फॉर कैरी लॉजिक उनके लिए आप कॉमन पाथ आइडेंटिफाई करोगे। देखो अभी यहाँ पे आइडेंटिफाई करेंगे। इफ आई चूज टू बी, कैसे कहाँ से लाऊं मैं, आई एम नॉट गेटिंग। ओके, चलो ठीक है, यहाँ पे मैं बात करता हूँ सिर्फ, अगर मैं पाथ चूज करता हूँ फॉर PMOS, ए बार ए बी बी बार, ओके, तो आई कैन गो फ्रॉम दिस लाइन, दिस पार्ट ऑफ द ग्राफ, ए बार ए बी बी बार। ओके, यहाँ पे मैंने जो कॉमन पाथ लिखा है उससे अलग है, यू कैन हैव मल्टीपल कॉमन पाथ। अगर मैं यहाँ से ट्राई करूँ इस मिडल पॉइंट से, ए बार बी ए, ओके, a bar b bar b a, definitely I can go for it। okay, do remember that very important rule is you can travel one path, one line only once। अगर a को आपने एक बार ट्रैवल कर लिया तो फिर से आप a के थ्रू नहीं जा पाओगे। ओके, every line, every node is traveled, can be traversed only once, तो उससे आप कॉमन पाथ निकाल सकते हो। अभी यहाँ पे मैंने ए बी बी बार ए लिखा है, ए बी बी बार ए, सो वी हैव ड्रॉन द स्टिक डायग्राम अकॉर्डिंगली। तो यहाँ पे ये जो सीक्वेंस ऑफ पॉलीसिलिकॉन है ना, बहुत ज्यादा इंपॉर्टेंट है। अगर आप यूजर्स पाथ फॉलो नहीं करते हो, यू कैन नेवर एवर कंप्लीट यूर स्टिक डायग्राम, कभी कंप्लीट नहीं होगी। You will have the confusion with the source and drain terminals of your design। तो आपको वो ध्यान में रखना है। यूजर्स पाथ जब भी आपके इनपुट ज्यादा होंगे वो आपको बहुत ज्यादा इंपॉर्टेंट है। दिस इज योर कंक्लूजन। लोड कैपेसिटर, तो भाई राइस टाइम फॉल टाइम कितना आया विदाउट लोड एंड विथ लोड, ये इन्वर्टर के लिए, नैंड के लिए, नॉर के लिए, और सम लॉजिक के लिए और कैरी लॉजिक के लिए। तो आपको ये सारा करना है। ओके, then moving on to next 2:1 multiplexer using logic gates and using transmission gate। okay, we will discuss about the using transmission gate, but using logic gate we can write down the equation like this। okay, can I have somewhere, yeah, fine। so अगर ये equation आप पढ़ोगे, whenever s is equal to 0 रखूं मैं, अगर s is equal to 0 है तो we will have y is equal to a, because this next term will go 0। if we put s is equal to 1, then this term will go to 0 and we will have y is equal to b। so this logic equation acts like a logic of 2:1 multiplexer। तो boolean equation है आपके पास, so whenever we will have the boolean equation, definitely we can draw the logic। okay, लॉजिक डायग्राम ड्रॉ कीजिए, यूलर्स पाथ फाइंड कीजिए एंड ड्रॉ द स्टिक डायग्राम। स्टिक डायग्राम ड्रॉ करने के बाद तो आपको पता है लेआउट ड्रॉ करना बहुत आसान है, जैसे दिख रहा है वैसे छाप दो, खलास। ओके, स्टिक डायग्राम तक बहुत इंपॉर्टेंट है। टू गेट द स्टिक डायग्राम वी नीड टू हैव द सर्किट। and the sequence of polysilicon. Okay, sequence of inputs. ये sequence of inputs कहाँ से आएगा? यहाँ से आएगा, देखिए यूलर्स पाथ से। तो वो बहुत इंपॉर्टेंट है। सीक्वेंस क्या है? ये ट्रांसमिशन गेट। अभी ट्रांसमिशन गेट को थोड़ा सा पीपीटी पे डिस्कस करते हैं। ओके फाइन। ट्रांसमिशन गेट, इसके लिए ना और एक टेबल है, NMOS and PMOS. We do have some poor, or I will say that bad. Let me change it to bad or good. Okay. So whenever we talk about the logic values of PMOS and NMOS, okay, how they transmit the logics. So NMOS is transmit bad one, whereas PMOS transmits bad zeros. Whereas NMOS transmits good zero and PMOS transmits good one. तो ये टेबल है। ये टेबल कहाँ से आया? This table comes from the device physics of your NMOSes and PMOSes. You need to read about it. But for now, I am giving this table as a thumb rule. Okay, NMOS अच्छा one नहीं transmit करता, it transmits good zero. Okay, so therefore, if you have observed, we always connect our PMOS bank in between VDD and output, whereas we connect our NMOS bank in between ground and zero, ताकि जब भी आउटपुट जीरो होगा, वो जीरो कैसे होगा? थ्रू NMOS होगा, सो वी विल हैव द गुड जीरो। जब भी आउटपुट वन होगा तो वन कहां से होगा? इट विल बी गेट कनेक्टेड टू VDD थ्रू PMOSes, it will be good one. What do you mean by good one and bad one? Okay, good one means it is 5 volt. Bad ones means it is 4.7 volt. Not exactly 5 volt. What do you mean by good zero and bad zero? Good zero is actual 0 volt. Bad zero is something 0.3 volt, near to 0 volt. Okay. So NMOSes gives you good zero and PMOSes gives you good ones. Therefore, we always have the CMOS logic in this way. This is also called as pull-up network, and this is also called as pull-down network.
Hello, sir.
Did someone? Yes, yes.
Sir, sorry to interrupt you. Sir, just need to ask this good and bad, is it similar to the strong and weak? The strong
Yes,
one and weak one?
yes, sir. Same names.
Okay,
This is
okay.
a weak. This is weak and this is strong. Yes, definitely. Okay. So transmission gate. अभी अगर मेरे पास समझ लीजिए, this is some logic 1 and this is another logic 2, and I want to transmit certain signal from logic 1 output to the logic 2 input. Okay, what I will do to retain the voltage levels, I will insert one transmission gate over here. So how this transmission gate looks like? Transmission gate. So it is a parallel combination of the PMOS and NMOS. ये PMOS ड्रॉ किया और ये NMOS ड्रॉ किया. Okay, इन दोनों का parallel combination है. So instead of drawing every time this way, we usually draw it this way. Okay, this is input and this is output. So if logic 0 comes in, your NMOS is going to provide good logic over here. If logic 1 comes in, okay, your PMOS is going to provide a good logic at the another side. So we are transmitting the logical values, logic 0 and logic 1, through our transmission gate. PMOSes will give you good 1 and NMOSes will give you good zeros or strong zeros. Okay, so this is a transmission gate. and the same thing is drawn over here in the Word document. कि भाई, let us analyze this schematic. Okay, schematic को analyze करेंगे कैसे? Let us see. Let me go back to PPT and escape. Okay. What happened? Something. One moment, please. Control से जाने दो. ठीक. So what I want to have, अभी A और B इस schematic ने ना act करना चाहिए 2:1 multiplexer जैसे. If we apply S is equal to 0. Okay. If we apply S is equal to 0, मतलब यहाँ पे क्या आया? 1 आया. यहाँ पे क्या आया? 0 आया. यहाँ पे क्या आया? 0 आया. यहाँ पे क्या आया? 1 आया. Okay. Now 1 is connected to gate terminal of PMOS, means this PMOS is off. 0 is connected to gate terminal of this NMOS. This NMOS is off. In turn, this complete transmission gate is off. 0 is connected to gate terminal of PMOS. This PMOS is on. 1 is connected to gate terminal of NMOS. Okay, this is on. Therefore, in turn, this complete transmission gate is on. So we can say that if S is equal to 0, Y is equal to B. Let us analyze the same way. What if S is equal to 1? Let me have some different color. Okay, great. Now if S is equal to 1, this is going to be 0. This is going to be 1. This is going to be, since S is connected to PMOS, this is going to be 1. And since here we have S bar, this will be 0. So 0 is connected to gate terminal of PMOS. Let me erase the previous. Okay. Now 0 is connected to gate terminal of the PMOS, so this PMOS is on. 1 is connected to gate terminal of NMOS, so this NMOS is on. Therefore, in turn, this complete transmission gate is on. 1 is connected to gate terminal of PMOS, so therefore this is off. 0 is connected to gate terminal of NMOS, this is off. So in turn, this complete transmission gate is off. So therefore, we can say that here we will have Y is equal to A. So after analyzing the schematic, we came to know, okay, this schematic somehow behaves like a 2:1 mux. And yes, we can use this schematic for implementing the same. तो थोड़ा सा उसको modify कर दिया. क्या modify किया? इसको यहाँ से break कर दिया और इस B को लेके गए यहाँ पे. So you can see we have the schematic in this way. ट्रांसमिशन गेट 2:1 मल्टीप्लेक्सर के लिए जैसे स्कीमेटिक दिख रहा है वैसे के वैसे ही आप लेआउट ड्रॉ करोगे. यहाँ पे पॉलीसिलिकॉन को अलाइन मत कीजिए, बिकॉज whenever we will have Boolean equation, then and then only we are going to align the polysilicon. अभी यहाँ पे S बार है, यहाँ पे S है, यहाँ पे S है, यहाँ पे S बार है, and you do have the overlapping in between the PMOSes and NMOSes. You do have A and B. Okay. Accordingly, you are going to draw your layout. Okay. ऐसे stick diagram दिखेगी. A, Y, B, S bar, S. So how your layout will look like? Let me show you the demonstration. Let us go and mux transmission gate open. This is how your layout will look like. A लगाया है, out लिखा है, B लगाया है. You do have S bar S. Am I right? S bar S and S bar. I want to show you important thing over here. Everyone pay attention. Okay. I will remove this all select lines inputs. तो मैंने इनको निकाल दिया. I want to show how we are applying those. Let me delete. Okay. Now looking at the diagram, here we do have S and here we do have S bar. Fine. Take your I put it over here. Okay, apply clock. I am going very slowly. Slower your clock signal. Okay, and I have applied S only. तो यहाँ पे S attach किया. Okay, अभी देखिए I will pick up once again visible node. I will place it over here. I want the S bar signal. I will go to clock और यहाँ पे एक ऑप्शन है इन्वर्ट लास्ट क्लॉक, उसके ऊपर क्लिक कीजिए. ओके, उसके ऊपर क्लिक कीजिए so that you will have your signal and assign. तो यहाँ पे ये इन्वर्ट आ गया. ओके, इसी को आप कॉपी कीजिए. एस बार चाहिए था मुझे यहाँ पे और मुझे एस चाहिए था ऑन दिस साइड. व्हाई आई एम डूइंग दिस वे? बिकॉज आई डोंट वांट टू mess with I don't want to mess with the timings of the clock signals. Okay, वो टाइमिंग सारे के सारे सही सही होने चाहिए. इसके लिए मैंने ऐसे सब कुछ किया. आई विल शो इट वंस अगेन. ओके, इंपॉर्टेंट टाइमिंग के लिए इनको फिर से मैं रिमूव करता हूं. ओके, विजिबल नोड, कीप इट ओवर हियर, गो टू क्लॉक, मेक योर क्लॉक अ लिटिल स्लोअर, 25. ओके, गिव अ नेम एज फाइन, असाइन. मैंने फिर से विजिबल नोड लिया, यहाँ पे अप्लाई किया, went to clock tab and click on invert last clock. invert last clock पे जैसे ही क्लिक किया तो देखिए यहाँ पे चेंज हुआ. लेवल 0 क्या है? 1.2. लेवल 1 क्या है? 0. इन्वर्ट हो गया. assign. ओके, and just copy these signals onto the required polysilicon. इनको आप ऐसे पिकअप करके लगा सकते हो. And applying the input and output, you know all the things. Okay, so I will open it once again and let us simulate it. Let me change the time scale and we will reset our simulation. Sorry. So looking over here, we do have A, we do have B. You can see the frequency difference in between the A. Then we have the S, okay, and we have output. So whenever S is equal to 0, we have B, and whenever S is equal to 1, we have A. Whenever we have S is equal to 0, output is equal to B. Whenever S is equal to 1, output is equal to A. Same way the way we discussed. Okay. One more important thing I want to make you notice over here. यहाँ पे अगर मैं देखता हूं तो मैंने एक यहाँ पे नॉट इन सिमुलेशन करके रखा है. ओके, अगर यहाँ पे देखता हूं तो विजिबल इन सिमुलेशन मतलब क्या? अगर मैंने यहाँ पे विजिबल इन यहाँ पे किया विजिबल इन सिमुलेशन, इफ यू गो इनटू द सिमुलेशन you will have S as well as S bar, both the signals visible. I don't want extra waveform in the simulation. So whichever waveforms you don't want in the simulation result, just go to this option, edit option, double click on the signal name and click on this visible in simulation. After clicking, it will be not in simulation and you can have a very neat and clean simulation result. Okay, everyone got it? This was a simulation for your transmission gate and this is a layout. Okay, now moving on to next experiment, that is the last experiment, that is SRAM cell. And as usual, the last experiment is always the difficult one because you have to use the understanding of all the previous experiments while implementing the last experiment. So this is a SRAM cell. Okay, यहाँ पे अगर आप देखोगे तो you do have back to back coupled inverters. मतलब यहाँ पे एक PMOS and NMOS यहाँ पे connected है एक दूसरे के साथ. Let me have the screenshot in the PowerPoint. Am I audible?
Yes, sir.
Okay. Fine. Okay, great. One moment, please. Okay, now you can observe that here. कहाँ पे गया draw? Okay. So we do have one inverter on this side, PMOS and NMOS. Okay, we do have another inverter on the left hand side, one PMOS and it is connected to NMOS. तो ये inverter आ गया आपका, am I right? And if you observe now very carefully, we do have its output. Its output is getting connected to the input, or iska output it is getting connected to the input. This is called as cross coupled inverter. Okay, cross coupled inverter. Output of one inverter is connected to the input of another inverter. Okay, these are called as access transistors. Matlab kya? This is a SRAM cell. Okay, whenever we want to write some data or read some data to the cell, then we have to write it or read it from these MOSFETs. These are called as access transistors. Okay, all these are called as access transistors, and those has to be enabled while reading or writing into the cells, SRAM cell. Okay, then how to turn on these cells or access transistors? Whenever word line is equal to 1, okay, whenever word line is equal to 1, then and then only your word line is equal to 1, then and then only these access transistors will be turned on. Theory बता रहा हूँ, क्या theory है? First, cross coupled inverters. Okay. Second, we will have access transistors. MOSFET को हो या transistors को. We can activate access transistors if word line is equal to 1. Okay. अभी ये जो bit line and bit line bar है. Okay. These two lines are used for writing or reading operation, both. Okay. अगर write करना है, we will apply some logic. Apply logic. कब? जब write करना है. अगर यहाँ पे लॉजिक 1 अप्लाई किया है तो लॉजिक 0 यहाँ पे अप्लाई करो. बट इफ, इंपॉर्टेंट पॉइंट, बट इफ वी वांट टू परफॉर्म अ रीडिंग ऑपरेशन, वी हैव टू राइट के लिए अप्लाई लॉजिक और रीडिंग के लिए you have to put your BL and BL bar in a floating mode. Microwind में you can apply 0 logic, you can apply 1 logic, also you can apply floating X. X अगर लिखते हो तो वो होता है floating. आपकी जो bit line है और bit line bar है which are complemented to each other, वो floating हो गए. कब करने हैं? रीडिंग जब करोगे आप तब की बात है. ओके, तो point number 1 cross coupled, point number 2 access transistor, point number 3 those can be turned on using WL is equal to 1. BL, point number 4, BL and BL bar lines are used for writing and reading purpose. While writing data into the SRAM cell, we have to apply the logic. While reading the data out from the SRAM cell, we have to put BL and BL bar lines in floating mode. Okay, everyone got it? These are very, very important points to perform SRAM experiment. Now looking at the diagram schematic itself, we are going to draw a stick diagram. जैसे schematic दिख रहा है वैसे ही draw करना है. Okay, so inverter है तो इसलिए 2 line straight forward आ गई. ये जो है आपके polysilicon, these are for the WL, that is your access transistor, word line transistor. इसमें है ना बहुत बहुत सारी चीजें होने वाली है, and just give me only 10 minutes and within 10 minutes we will end our simulation as well. Let me show you SRAM का layout कैसे दिख रहा है. ऐसे दिख रहा है. Now यहाँ पे थोड़ा सा अलग दिख रहा है आपको, ये पिंक पिंक दिख रहा है. Am I right? Okay, let me remove the capacitors from here. Okay, now what is this pink? Okay, do remember that this is the output of the right hand side inverter. Output is connected to the input of another inverter. This polysilicon is nothing but inverter. Let me demonstrate that connection over here. So if we have a polysilicon and if we have a metal, and if we want to connect the two, just merely putting this much will not make the contact. कांटेक्ट नहीं होगा क्योंकि पॉलीसिलिकॉन का प्लेन अलग है और मेटल का प्लेन अलग है. Let me try on this side. Let me put the polysilicon. I want to connect the polysilicon with the metal. Okay. अगर यहाँ पे मैं कट देता हूँ तो you can see concentrate on the red, this is polysilicon. Concentrate on the blue, this is metal. There is no connection in between over here. Okay, there is no connection. Those are different layers inside your processor, inside your design. But as soon as I have a contact over here, contact metal to poly in the palette, I take it and I keep it over here. Okay, and I stretch. Okay, no problem. Then I once again give a cut at this point. Can you see the dotted line? Okay. So I am cutting our layout at this line. So you can see now this polysilicon and this metal is connected through via after placing the contact. Okay. And this contact looks like pink in color. Okay. So whenever we want to have the connection in between the metal one and the polysilicon, we need to put the contact, and that contact looks like a via. तो वो cross section view मैंने आपको दिखाया. We will go back to our design SRAM. Okay, once again I will remove the cap. Okay, so now here we do have lots of things going on. So we do have connection between VDD, we have connected output to the input and similarly output to the input. We have given Y and Y bar as a name. We have WL, WL, same signals over here. देखो 0.99. Okay, यानी यहाँ पे भी 0.99. टाइमिंग सेम होना बहुत ज्यादा जरूरी है. नाउ द मोस्ट क्रिटिकल पार्ट जो मैंने कहा था कि भाई BL बार आपका समटाइम्स फ्लोटिंग रखना है, समटाइम्स यू हैव टू अप्लाई द लॉजिक. वो कैसे करते हैं? लेट अस लुक इनटू BL. देखिए यहाँ पे पढ़िए. हाँ, ये यहाँ पे मैंने क्या किया है, पल्स विड्थ सिग्नल दिया हुआ है. ओके, PWL सिग्नल. 0 नैनोसेकंड पे BL है 0, 1 नैनोसेकंड पे BL है 0, 2 नैनोसेकंड पे BL है 1, 3 नैनोसेकंड पे BL है 1 एंड 4th नैनोसेकंड पे BL है फ्लोटिंग. उस पे अगर आप डबल क्लिक करते हो ना तो यू कैन चेंज द वैल्यूज. यू कैन टाइप x. 5th नैनोसेकंड पे है फिर से x, मतलब फ्लोटिंग. मतलब क्या हो रहा है, फ्रॉम 0 नैनोसेकंड गोइंग अप टू 3rd nanosecond, 3 nanosecond, we are writing the data, and from 4th nanosecond to 5th nanosecond, we are reading the data. Now observe over here. पहले 0 write किया, 0 write किया, 1 write किया, 1 write किया, and then we are going to read the data. तो 1 write किया था at the last moment, so we will have 1 at the output. Okay, so the way we did in the BL, same way we will do in the BL bar. BL bar में क्या होगा? Let me have the screenshot. Let me put it into the slides. Okay, so this is a signal value for BL. Am I right? What will happen in BL bar? So at 0 nanosecond we will apply 1, at 1 nanosecond we will apply 1, at 2 nanosecond we will apply 0, at 3 nanosecond we will apply 0, at 4 nanosecond and 5 nanosecond we will keep BL bar also as floating. X का मीनिंग क्या है? फ्लोटिंग रखनी है आपने वो लाइंस. ओके, We will check whether we have really done for applying BL bar in our layout. Cancel and let us go for BL bar. Okay, देखा 1 1 0 0 और बाद में floating रखा है. Okay, now let us try to simulate our design and what happens really. I will explain you the simulation result. Let it get complete. Okay, now I will take the screenshot. Fine. Okay, we will do it afterward. WL, एक WL को निकाल देता हूँ simulation से. WL दो हो गए, निकाल दिया. Assign. Okay, great. Okay. Now BL is equal to 0, and whenever your WL is going to be 0, your Y is going to be 0. Let me show you the diagram. Layout ही दिखाता हूँ. देखो ये जो Y लिखा है यहाँ पे Y bar, these are the values which are getting written. WRITTEN लिखी जा रही है जो values आपके सेल में, वो values indicate करती है. अगर BL 0 है तो Y भी 0 होना चाहिए. अगर BL 1 है तो Y भी 1 होना चाहिए. Let us check whether this is happening in the simulation or not. Okay, so BL here, can you see the yellow line? BL is 0, and whenever WL is equal to 1, your Y is 0. So whenever WL is equal to 1, your data will be written, WRITTEN, written inside the cell. Since BL is equal to 0, WL is equal to 1, therefore Y is equal to 0. Here BL देखो बाद में 1 हो रहा है. BL is equal to 1, WL is equal to 1, therefore Y is equal to 1. The BL values are getting written, WRITTEN, written inside the cell. Okay. बाद में ये yellow के बाद white दिख रहा है क्या आपको? I am not sure. Let me put it into once again PPT so that I can zoom in. Okay. How I can zoom in now? Let us have the paint. Okay. Now can you see that yellow line is getting gray in color? Someone say yes. Hello. Hello.
Yes.
Okay. So yellow was something 1 1, logic 1 1, and this gray is your floating. Okay. So BL is getting your into X value as well as your BL bar is also getting into X value. Since it is a white to gray transition, it's not visible here, but it is more clear in BL line. BL is getting gray from yellow. Get us back to simulation results. Okay. From this point onward, 4 nanosecond. Okay. 4 nanosecond के बाद आपका BL जो है वो floating है. Therefore, now we are doing reading operation. And what was the last value which we wrote inside the cell? That was a BL is equal to 1. That is your Y is equal to 1. Therefore, even if we are putting our BL value in the floating mode or floating value, our output stays 1. Your value, the previously wrote value, got latched inside the cross-coupled inverter. Okay, so if we change the value afterwards, definitely accordingly we can see the effect on the output Y. Output Y is used to write to see the values inside the cross-coupled inverter, that is your SRAM cell. Okay, ये starting में जो glitches आ रहे हैं, those are due to the internal capacitances of your devices. बहुत सारे parasitic capacitances होते हैं, diodes होते हैं, transistors होते हैं, everything you do have inside the MOSFET. Okay, due to those get stabilized in the starting few nanoseconds. It takes around 0.3 or 0.2 nanoseconds to stabilize its voltage values. Therefore, we do have spikes over here. Okay, so SRAM cell takes a lot of time to draw the layout. Okay, and that is the hardest experiment to explain as well. Okay, layout draw करने के लिए भी time लगेगा और explain करने के लिए भी time लगेगा. So this is all from my side. Let me have some questions from your side, if at all you have.
Excellent, sir. Excellent session. So I request the student participants, if there is any question, you can ask your questions.
You can definitely ask sir exam में क्या पूछा जाएगा वो भी पूछ सकते हो. Sorry.
Yes, students, any question?
I guess they might have got a little bit bored in the last experiment. Yes, Ram.
Okay, we will ask in the other way. Students, have you understood it? Have you understood this?
Yes, sir.
That is an affirmative question.
Yes, sir.
And the next counter question comes in, students, whenever we say that yes we have understood, the counter question is like, what do you have understood? Okay, great, fine. That's all from my side. Everyone, all the best for your examination, and do prepare in well manner. VLSI is a very, very interesting subject, and if once you understand it, you will start liking it, definitely, for sure. All the best, everyone.
Yes, sir. Over to you, Prashant sir. Prashant sir, just give the vote of thanks.
Thank you, sir. Thank you, ma'am, for the opportunity. So before going to the last part of the session, I would like to summarize the session. The session started with the great video of Intel indicating the fabrication of chip. Then sir has rightly explained some techniques like what is the 3D view, what is top view, the dimensions, channel length, complementary MOSFET, and everything. So students, hope you have gained some knowledge out of it. And then the remaining half session was based on the practical, so where different experiments were demonstrated live through a simulation. So thank you, sir. It was an excellent session, and hope students have gained a knowledge out of it. So on behalf of ENTC Department, Diva Patel College of Engineering, Akodi, we would like to have a sincere gratitude from our side to you. Thank you, sir. Thank you very much.
Sir. Thank you, sir. Thank you, ma'am.
Thank you so much, sir. Yeah. It was a really excellent session. It was informative and knowledgeable also. And patiently and means the presentation which you have made, it was really up to the mark. Thank you so much. And really our students will get the benefit out of it, because not only you have put your efforts to explain the theoretical and the practical aspects, but also you have covered what are the opportunities for these students to go for this in a VLSI field in future.
Yes.
Thank you so much, sir. Yeah.
Thanks a lot, everyone. Take care. Bye-bye.
Yeah, thank you, sir. Thank you, ma'am. So with this, we